objectives. What is the project? What is the partnership? I will tell about the mapping, the case studies, the other BioFit activities, and as an introduction to the 2 industry sessions which will happen today. This is a very nice picture here. We took that on a meeting when it was still allowed in ancient times, 2 years ago, when this is the Ptolemaides 5 600 megawatt power station, which is under construction, and it will likely to work on coal until 2025 or maybe 2028, but then there will be a Greek coal phase out and other means of energy generation will be needed. So that was a very powerful and visible reminder of the transition which is we are undergoing. I don't think I tell a lot of news when I say that even in 2018, still 58% of the EU's renewable energy in 2018 was from bioenergy. That's 10% of the total energy consumption. And I like this very much, this timeline. If we divide the energy consumed in the EU in a year, and we start with fossil fuels on the 1st of January, then by the 20th of October, we run on renewables, and already on the 19th of November, we run on bioenergy only. And that means we still have a long way to go, but we are making substantial steps. And in those substantial steps, bioenergy is playing a large part. It will likely continue to play a large part. The IEA says so much in its roadmap, and also more recently, EU in the taxonomy has said that bioenergy is not a transitional fuel, but it will remain an important fuel, especially for the more difficult to carbonize sectors. Bioenergy retrofitting, the subject of the project, that is a relatively easy way to replace fossil fuels or outdated renewable technologies. And it is, of course, it's easier often than build greenfield plants, because it is you can keep part of your plant and you have shorter lead times, lower capital costs, faster implementation, less production time loss, and lower risks. So our overall objective is to facilitate the introduction of bioenergy retrofitting in 5 exemplary industries: first generation biofuels, pulp and paper, fossil refineries, fossil-fired power, and combined heat and power. And you will see this division back in our 4 industry sessions. Here we have 1 on each sector, with the exception of fossil-fired power and combined heat and power, because it turned out that it was more or less very similar. So we combined that one. The project is nearing its end. We had a 3-year project where we worked together with 14 partners on the facilitation of the bioenergy retrofitting. And you see we had a quite good division across the various European countries. We've done a lot, I think, in those 3 years. We have developed existing retrofit examples. We made very nice fact sheets. We made a handbook, which you can download from the website, where we, in that handbook, we make a catalog of all the existing retrofit options in these 5 industries. And there are quite a lot of opportunities. We have a very nice industry map showing a number of retrofitted plants, and that's also quite a lot. And very soon a set of digital support tools to quickly check whether a retrofit is good for your industry, for your plant, will be available on our website as well. We've done a lot of work to develop case studies with industry. we have developed 10 case studies in which we look at a specific retrofit option together with an existing industry, with a market player. Has 2 for 1G biofuels, 2 for pulp and paper, fossil refineries, and fossil-fired power combined heat and power. In the industry sessions, a lot more will be said about it, so I won't say too much. Save for the overall conclusions that what we see is that there is really a very big, wide variety of technological options for bioenergy retrofitting, making a spectrum of high-value products in a number of ways, which are often really also quite economically feasible and are really actually implemented. Nearly all the case studies show that you can economically feasibly retrofit, and also that it results in a significant capital expenditure reduction of around 50%, sometimes higher. So that's you will see this these overall conclusions reflected in the industry sessions. We've done other things. We've looked at the framework conditions, looking at actual barriers. We also looked at acceptance of bioenergy, which is an issue which we as industry have to confront, and we will continue to confront it. And of course, we provide advice to policymakers. We will have on Thursday a policy breakfast where we give our policy advice, and we hope to also get input from you all on what it is, so that everybody can learn from that. Of course, we have supported informed, facilitated dialogues with industry in various ways. With respect to acceptance, we have done a very nice survey on 32 members of the public in 4 countries. And one of the very nice highlights, I hope that it comes back in the final conference in some way, but a very nice highlight was that the public acceptance of bioenergy was in all those 4 countries quite high. This is a scale of 1 to 6, and it's between 5 and 6. There is not much difference between the countries. It's almost all quite good. But if you're talking about companies behind it, it's quite low. So here you see directly that the industry has something to do. There is a very good, fertile ground for public acceptance, but it's the way in which we communicate about the technology options and about what we can do with our technologies. This ends my presentation. Today we will go to 2 industry sessions. One is about the fossil-fired powered and CHP. That will be moderated by Manolis Karampinis of SET. So I will give him the word in a few minutes. And after that, at around 3:15, then we will have the session on bioenergy retrofitting in fossil refineries, where I hope to see you back again. This concludes my introduction. I wish you all a very good conference, and I hope that it will be useful and a good learning experience for everybody. Thank you very much.
Thank you, Patrick, for the introduction. I think we can start on the first industry session of the day, and I will share my screen in a minute. Sorry. Is it visible? And in full screen mode?
It is visible, but not in full screen mode.
Now it's in full screen
now,
mode.
yes.
Yeah.
Perfect.
Okay, perfect. So, as Patrick said, my name is Manolis Karambinis. I'm a chemical engineer and a research associate at Center for Research and Technology in LAS. And in the last 3 years, I had the pleasure of working in the BioFit project, serving as what we call internally the sector expert on the fossil firing power and CHP sector. And in this particular presentation, I will mostly focus on one particular aspect of this sector, the large-scale coal to biomass conversions. I would just like to add here that, of course, there are other possibilities for decarbonizing the heat sector or the power sector. We have done some investigations in the project. One could use, for example, bio-oils, or even syngas or other possibilities. But for the most part, I will be speaking about the replacement of coal with solid biomass. And I think most of you are quite familiar with the term biomass co-firing. It's a technology that has been around since the early 90s, if not earlier, in Europe and beyond. Occasionally, we still see some, let's say, question marks about why we are talking now about conversions and why not just standard co-firing with coal. I would say there are two main parallel reasons for that. The first, of course, is the political will to phase out coal in the European Union. You can see that in the map on the left of the slide. And in fact, many countries already have either phased out coal recently. Many others are committed to phasing out coal by 2030 or earlier. However, there is, I would say, still a part of Europe, especially the eastern and southeastern parts, where there is still significant coal generation taking place in the electricity sector, and the decarbonization options there will be a much more critical aspect of the overall discussion in the future. The other main reason has to do with the latest directive on the renewable energy, the so-called RED II, where one of the requirements that has been introduced about the electricity from biomass has to do with the fact that biomass should be now the main fuel and not the fossil fuels. And essentially, these rules are, I would say, the less ambitious versions of co-firing which were implemented in the past. Why would someone look into the coal to biomass conversion? If we're talking about benefits, there are several, let's say, there are several of those. For utilities, I think one of the main reasons, we will hear more about this later, is the utilization of otherwise stranded asset. If you have a large coal power plant, it was a huge investment. It has infrastructure in place, a grid connection, the boiler, turbine, and other things that you would not be using anymore if you're not doing something with the plant. Of course, when you're switching from coal to biomass, you're generating renewable electricity and you decarbonize your electricity generation mixture. And this also comes with some financial motivation, usually some kind of feed-in premium, the reduction or even the minimization of the CO2 cost, and so on. There are some advantages for the grid operators as well, because the big biomass power plants is still a dispatchable thermal power generation, and with the phase out of the coal, and in some countries, especially in Germany, the phase out of nuclear as well, this is starting to be in short supply. And increasingly, this is a role played by natural gas in the electricity mixture, but biomass power plants can somehow diversify this requirement. And when it comes to societal benefits, I would say most of the support here is in the local economies, especially in transition regions where coal has been extracted and converted into electricity. The phase out of coal is a significant loss of jobs for those areas. And if there are some solutions which allow local job retention, then of course it's something that especially the local population, I think, and local politicians look upon favorably. When it comes to technology, I don't have a lot of time to speak about in details. I would say that at the last stage of the project, we mainly found that there are three groups. The first one is the retention of the typical technology used in large-scale coal combustion, the pulverized fuel technology. And this is something that has been applied into boilers with a fuel input of up to 1,000 megawatts or even more. There are some modifications required. I think one of the main ones in most systems is that you have to change the milling system to change from the coal fuel to a biomass fuel that has a different behavior. Sometimes you have to install new burners. You may do some other adaptations in the flue gas cleaning equipment or the combustion control, but you also have to take care about the biomass handling and the storage issues. The fuel used in these conversions is primarily wood pellets, and this has to do with the large-scale supply issues. When you're requiring biomass volumes for such a big power plant, you must need a high energy density fuel. At the moment, this can only be provided by the wood pellet market. And now there are several references of such plants that have been converted. Another option, which has also attracted a lot of attention, is the conversion to thermally treated wood pellets. Essentially, you have a fuel there, which is biogenic in origin, but pre-treated to resemble coal, so that there can be a substitution with minimum modifications required. It's a promising technology for sure, but at the moment has only been applied commercially in one power plant in Canada. Some other projects or small-scale demonstrations have took place. So it's a little less mature, and also the biomass, the market for the thermally treated pellets is still not mature at the moment. And the final option, which we identified as especially suitable for smaller scale units, is the conversion into a bubbling fluidized bed. And essentially here you change the combustion system, you stop firing pulverized biomass, and you have a fluidized bed regime. Several modifications in the boilers are required, but then the advantage is that you can use a wide range of local and traditional, we say, biomass feedstocks, such as forest residues. Perhaps you can use a certain amount of agrobiomass or waste, but with minimal processing. So it's a good option for shorter supply chains. And again, several references. There are many factors that a utility will have to consider before embarking on a conversion. I don't have the time to go into a lot of details, but of course, the on-site site infrastructure has to be assessed. The fuel sourcing options need to be considered. The logistics infrastructure for bringing the fuel to the boiler house have to be considered. Health and safety aspects, the support scheme that will allow the conversion to take place. And in the future, there are other possibilities such as biomass carbon capture and storage that might allow a longer-term perspective for these technologies. At the moment, I think there are a little over 4 gigawatts of active good pellet conversion projects in Europe. Most of them are in very specific countries. UK is the clear leader with projects like Drax and Linemouth, but there is also some capacity in Belgium, in Denmark, and in the Netherlands, and some smaller ones in Sweden. If you look at I would say, the combined statistics, it can be estimated, I think, that on the EU27 level, about, I think, 5% of the biopower supply is coming from such converted plants. It's a little different story in the UK, where about 50% of the bioenergy supply is provided by those converted power plants. And as you can see here, most of these conversions took place around early 2010s or so, and up to 2019, more or less. And so some of them have been active for quite a few years already. And most of them, I think, have a quite interesting history, which is not, we don't have the time to go into details, but for many of them, the biomass users did not take place from 0 to 100%, but gradually. Some years ago, when back in November 2019, we had an industry forum in the BioFit project about repowering coal plants to biomass. It was at the time, as Patrick said, that were an ancient history when we were allowed to travel. And at that meeting, we had identified through a preliminary reading of the draft National Energy Climate Plans that by 2030, more than 80 gigawatts of coal plants plants were to be decommissioned in Europe, probably even more now with the more advanced coal phase-outs. At the time also, there were many discussions about conversion projects that were considered in Italy, in Ireland, in Greece, Spain, probably elsewhere. But since that time, almost nothing happened in developments. And why is that? I think the main reason has to do with the controversies associated with the wood pellet combustion in large-scale power generation. It's a topic that it's too lengthy to go into a lot of details here, but I'm sure all of you are familiar that it has been reported quite extensively for such a specialized topic in the news. Also has been targeted explicitly by several NGOs who are attacking the sector, and so on. It's very difficult to get into such a lot of time, such short time, into the arguments that these people are bringing, what are the counter arguments to them. But I would say the major implication here is that all this discussion has spilled over into the policy sector, and the policy updates we are hearing from Brussels tend to impose more and more and stricter requirements. Whether these are reasonable or not, you will hear more soon in Bioenergy Europe's presentation. But I think this has been a showstopper for many utilities to consider conversion plans. Before concluding, I would like to summarize some cost factor in conversion projects, because at the end of the day, the energy sector is a lot about the costs and the money. And in such conversion projects, I think there are two main factors. The first is the CapEx, the capital investment. And if you look at some figures we managed to compile from different public sources, the conversion cost for many big power plants has been around from 125 to a little over 800 euros per kilowatt electrical, which is, of course, much, much cheaper than new biomass power plants, which can be from 2,500 up to more than 4,000 euros per kilowatt electrical. In comparison, however, because again, as I said, it's always about cost, it's, I think, quite comparable to the cost of a new natural gas CCGT plants. So the capital requirements are, of course, much smaller if you are considering a biomass option, but comparable, I would say, to other fossil fuel options now on the market. But it's also very interesting to see what happens on the fuel cost and the impact on the electricity price, because that's the main, at the end of the day, driver on the electricity price. And here, if we're looking at the wood pellet prices, there have been spot markets from 120 euros per ton back in last summer to more than 200 euros per ton this December, also affected in some extent by the overall increases in the energy prices. If we assume a 40% net efficiency, then the electricity production cost from the fuel alone is from 63.5 to 119 euros per megawatt hour. And until recently, we always used to say that if you wanted to have a conversion, then you needed a kind of subsidy scheme to make it happen. However, I would say it's very, very interesting to compare those prices with the current electricity prices now, which are mostly driven by the large increase in the natural gas price. So in the current, I would say, energy price framework, a conversion can be all, I would say, subsidy-free if this persists in the future. And of course, there are different initiatives. For example, Drax has a structural initiative to reduce its electricity cost up to £50 per megawatt hour by 2027 through increased self-supply, broadening the fuel envelope, and so on. So there are several developments here that might push down the costs even lower. When it comes to the Biofit project, we have been working on 3 case studies on coal to biomass conversions, and they were actually quite interesting and variable sets. 2 of them were located in Bosnia, so a country that is still out of the main European Union policy framework, but affected with it. Cities aspires to become a member. And one is in Italy, in Sardinia especially, where it was very, very interesting to see how a coal to biomass conversion could fit into the framework of an island energy system. But I won't say more about this because the case study companies will give their own insights in their presentations. So I will stop here and I will resume at the end of the session with some policy recommendations we have drafted in the project. And then I will give the floor to Gilles Gauthier from Bioenergy Europe. He is the policy development director, if I'm not sorry, the market development director, and one of the main persons I think to be discussing about solid biomass utilization in the organization. So, Gilles, the floor is yours.
Thank you very much, Manolis. Good afternoon, everyone. I hope you can see and hear me good. I'll now share the screen, and then we can get started. Can you confirm that you can see the presentation here?
Yeah, we can see it.
Yes.
Okay, very good. So again, good afternoon, everyone. Indeed, I wish that we would have had the opportunity to meet in person and not remotely like this, but I guess we have to go through this additional wave, hopefully the last one, and I hope that all of you are basically healthy at your own place. So indeed, my name is Gilles Gauthier. I will give the first part of this presentation, and then my colleague, Daniel Reinemann, will take over for the policy part. So I will take care on my side about the let's say market aspects. So first of all, a few words about Bioenergy Europe. I'll be very quick on that because I know that the time is limited. So we are a team of about 30 persons based in Brussels, and obviously our role is to protect the interest of the European bioenergy sector. We are existing for more than 30 years now, and we are made of 185 members, which might seem a lot for you, but actually, given all the challenges, including the one that Manolis has spotted with all that controversy that exists against biomass, there is definitely a need for us to get together and to be stronger and stronger. So on the roles or the services Bioenergy Europe is offering, obviously we're there first to analyze the EU policy and also to influence it. We are also collecting and publishing market data, mostly for our members, and most of what you will see today is actually coming from our statistical report. We also give some visibility for our members. We offer you networking opportunity, and all our events are for free. And we also team up with some other conference organizer to have our member enjoying some discounts. So here are the list of our members. If you are interested to join us and enjoy all the services we offer, feel free to get in touch with me, and I'll be very happy to give you more information about it. So first, I will give you a very, very quick European energy overview. But what I want to show at the end of the day is, as it was basically brought during the first speech today, indeed, bioenergy is definitely the biggest contributor to renewable energy. So altogether in the energy mix of EU, renewable is for about 20% of it, and within those 20%, nearly 60% of it is actually bioenergy. And then if we go deeper in this bioenergy part, you can see the fuel or the biomass feedstock we're basically using to produce this bioenergy. So for 10% of it, it's waste biomass. Then for 20% of it, it's agricultural biomass. And for 70% of it, it's woody biomass. So you see there that actually most of the fuel we're using to produce bioenergy is actually woody biomass, but agricultural biomass shouldn't be forgotten. Actually, when we look to the future and see where most of the potential for further growth is standing, we believe that agricultural biomass is definitely the part of our industry that will see the highest increase in the future. And so basically, we believe that most of the potential is there. Unfortunately, burning agrobiomass is coming along with challenges. No need to explain you that as you are a specialist. And I believe as well that given the tension we see on the woody market, I'm pretty sure that there is now a growing interest for the agricultural biomass. The only problem with this biomass is how to get proper data. It's already challenging to collect data on wood pellets. Wood chips, it's even more difficult than wood pellets. And then when you end up trying to analyze numbers on agricultural biomass, it's definitely challenging. Still, to come back to this picture, when I say that woody biomass accounts for 70% of the feedstock that are used for bioenergy production, you have also to break that up in the different, let's say, fuels, or in the different categories. And even though the wood pellets have a lot of visibility and gain a lot of traction, wood pellets are actually a minor part of it. So 8% only of the woody biomass that is used for bioenergy purposes is pellets. The rest, for nearly half is firewood and wood chips. So don't think that pellets is the biggest fuel we use. It's actually definitely the smallest one. So I will now give you a quick update on the pellet market, and then I will say a few words as well about the wood chips market. So the pellet market, we are definitely knowledgeable in Bioenergy Europe on that. We have one working group dedicated to that, which is meeting twice a year. And we have also a pellet report, which is made of more than 120 pages, giving a lot of details about the pellet production, pellet usage in the different segments, pellet price, and the sales of heating appliances. So if you want to get more information, I'll be very happy to give you more information separately. So first thing first, the thing we like to do is to draw this global pellet map, where you see that EU 28, we're still speaking about the EU 28 in this case, is a big player, let's say, both on the production, which are those green bar, and both on the usage, which are these red and orange bars. So you see that back in 2020, so nearly 2 years ago now, we produced 18 million tons of pellets, while we did use 28, which means that there is a gap that has to be filled by exporting countries or exporting regions. One of them is North America. North America, together US and Canada, is a big producer, and they export most of their production to us and also to Asia. And we can also have a look at what we call the other Europe, which are the European countries outside EU, including Russia, which is also an exporting region, exporting most of their production to us as well. And even though we are here in the middle of the picture with the EU 28, we are not the most dynamic market for some years now. Indeed, the most dynamic market, both in terms of production and consumption, is actually Asia, that you see on the right there. So they're producing nearly what they need. They still import from other Europe and North America. And when you go deeper into the details, you see that indeed on the production, it's mostly from Southeast Asia, Vietnam, Thailand, Malaysia, Indonesia, which is growing very quickly. And on the use side, it's mainly Japan and Korea, South Korea. And Japan is actually the one which is growing the most in terms of usage of wood pellets. So in a few years, they might reach 10 million tons of pellet usage in Japan. So I don't have much time to go deep into the details. So I will give you very quickly an overview of the industrial use of pellets in Europe this time. So what we consider industrial use in Bioenergy Europe is actually the large CHP, but also the power-only units. You can see here on the map the biggest player with the UK, the Netherlands, Denmark, Belgium, and Sweden. All of them show different development over time. Obviously, here you can see the 2020 figures, and down you can see the increase or the decrease from the 2019. So maybe a few words about UK. Obviously, UK, thanks to Drax, is definitely the biggest user. There are some more units coming online, at least one. So this number will even be higher in the future. For the Netherlands, I guess you recall that in the Netherlands they used to use pellets, and then it stopped for some time because of let's say a stoppage of the political support for biomass usage, and it has resumed a few years ago, and now it is continuing to increase with a limit that will be around 3.5 million tons in the future. And then Belgium should be mentioned as well. Indeed, we used to be a significant industrial pellet user, but this time is nearly gone now because the Rodenois, the Les Aouires, sorry, power plant has stopped the operation in September last year. And I don't know what will happen to the Rodenois one. So that means we lost already between 300 and 400,000 tons of consumption in Belgium, and the 900,000 that are left, at least for the industrial market, I'm not so sure about what will happen in the future for it. And very quickly on the market situation, I have to be very quick, sorry about that. On the market situation, the situation was rather, let's say, quiet. The market was rather quiet in early 2021. And then later in 2021, there has been a very big consumption of industrial pellets from the industrial users for many reasons. One of them being that the electricity price was rather high, making it profitable to run on biomass. So there was an increasing use of wood pellets for power production in most of the utilities, which has created a significant tightening of the market. So there is now a complete shift in a few months between the situation we had, let's say, until mid-21 and the situation we have now, where the market is rather tight, and it is definitely reflecting on the price of the biomass. Just a message to the organizer. I hope it is okay that I would exceed my speaking time of about 2-3 minutes. If it is not the case, let me know and I will try to shorten that. So if we look now to the future, we can see two countries where there might be an increase of the usage of wood pellets or woody biomass for heat and electricity production. One of them is Poland, because indeed they've committed to phase out the usage of coal, but their plans are unclear at the moment to me. But Germany is much more, let's say, likely to use industrial biomass in the future, not in conversion of power plant, to what I understood from a different expert, including Hawkins Wright, because there is no, let's say, no favorable policy framework for a conversion to biomass for electricity production, but there is one for biomass for heat. Indeed, if you look at this diagram here, you see that it is the heating structure of German housing stock. So basically where the heat is coming from for heating up the different households in Germany, and you see that for 40% of it, it's coming from district heating, and a rather significant part of those district heating, so nearly 20%, is actually relying on hard coal or lignite. And there is now a plan in place or there will be, sorry, soon a plan in place to support the transition from this lignite and hard coal to renewable solution, including biomass. So it might be that Germany will start using industrial biomass for heating purposes in the future. So I would like to say very quickly a few words about the wood chips market. Part of this information is coming from our member Cleantech Trade. So the situation is rather similar than the situation of wood pellet. The first semester of 2021 was very quiet. There was a lot of supply and I would say a reasonable demand. So there was an oversupply of wood chips and rather depressed price. And within a few months, there was a complete shift. Indeed, the supply was not as important as in the past, and the demand was much more higher, including for the reason I've already mentioned for the wood pellets, in the sense that the electricity price was rather high, allowing a larger user of biomass. On top of that, the CO2 price is definitely increasing, which is making it profitable as well. So we have a rather important shift on the market, which is bringing serious tension on the supply, and definitely which is then reflecting on the price, which is nearly my last slide. So if we look at the price now, you can see on the left side a nice illustration coming from Argus. I didn't use mine because this one has the added value to compare basically the development of the price of the wood chips and the wood pellets. And you see that there is a very important growth both for the wood pellet price and the wood chips price. But you have to bear in mind that those indexes or those spot price are only reflecting a part of the spot market situation. And a lot of the industrial players, they rely on mid-term or long-term supply contracts. So this kind of spot price index is mostly there to give market trends, but you shouldn't think that this is actually the price that every single market player is paying for the product. And I've discussed, and I had the opportunity to see a presentation recently from Suez, where they were showing as well a kind of recovery of the price of the waste woods as well. So very similar trend than the clean wood pellets and clean wood chips. I would like to conclude with one thing, which is the fact that even though you've got some fluctuation on the biomass price and unfortunately an increase those days, if you compare with the fluctuation you can witness on the fossil fuel, being the natural gas or the oil or the electricity, you see that we are much more stable and we will remain much cheaper. I will leave you with this expression from one of the speakers I met recently from EEX. He was saying that the wood pellets are basically the stable anchor in the energy complex. So that's the kind of message I like us to put forward. We are definitely cheaper than the fossil fuel, and we show also a great stability of price over time, even if at the moment we've got, let's say, a bit of an increase of the price of our biomass for the moment. So with that, sorry for having been a bit longer than expected. I will give now the floor to my colleague Daniel to take over on the policy part. Thank you very much.
All right, thank you very much, Jill. If you can go to the next slide. So I'm going to go through and present an overview of what the EU legislation is that's impacting the rules for bioenergy facilities today. And then after that, we'll kind of take a quick look at what we can expect looking forward to RED 3, what the legislative framework is going to look after the Fit for 55 packet in 2024, and then I will just discuss a little bit on what are some of our views and concerns looking forward. So if you go ahead to now. So looking first, one more. at the criteria in the Renewable Energy Directive. These criteria are very important for a number of reasons. So in order for biomass to be counting towards renewable energy targets, for sectorial sub-targets, in order for it to receive any kind of public financial support, and to maintain its zero rating in the emission trading scheme, it needs to adhere to all of these criteria. So these three criteria that biomass is required to meet there are certain sustainability criteria regarding the harvesting and the impact on soil quality to make sure that you're not having negative impacts on the environment. There are also requirements for land use change in forestry, the LULUCF requirements. This is ensuring that for the biomass that's being harvested and being used, that there is indeed replanting and regrowth happening to ensure that it's remaining carbon neutral, and that you have this regeneration or even growth in the carbon stocks to make sure that this is a sustainable solution. And then you also have the greenhouse gas emission savings criteria, which is requiring that there's a certain amount of greenhouse gases that are being saved compared to if fossil sources were being used, based off of the chain, the life cycle chain, looking at how those products are gathered and transported. So next. And, I do want to mention a couple of exceptions here. There are exceptions for if these fuels are being produced from waste or residues. In that case, you only have the greenhouse gas criteria and soil quality requirements for agricultural biomass. This is, acknowledging the fact that if it's coming from waste and residues, then the rest of those sustainability criteria are being taken care of other areas, and that this is a byproduct, and therefore it is not necessarily feasible to provide that information. There are also exemptions for small installations that are below 20 megawatts, and this is 2 megawatts for gaseous biomass fuels. And then there's also an exception for energy efficiency criteria that only applies to installations that are large-scale electricity over 50 megawatts, which I'll get to in a little bit. Next. And so when we talk about these criteria that they need to meet, one important thing is to consider how that compliance is going to be demonstrated. So the way that this is set up through RED 2 is that either member states can set up their own national schemes, which will go through and verify the sustainability of this biomass, or they can, private actors can rely on a voluntary scheme that's been recognized by the European Commission, and then these schemes will, be vetted and approved in order to guarantee that these criteria are being adhered to. The way in which these criteria work is that they approach this the sustainability of forest biomass through a risk-based approach. So this means that compliance can either be demonstrated on a national or subnational level, which is, looking at does a country have the right laws and safeguards and enforcement in place to verify that this is indeed the general practice and this is how things are operating within that country. Or if this is not the case for all levels of criteria, then this can also be demonstrated at the forest sourcing area level by going through and submitting the relevant data that would be needed to verify that as well. Next. So when we go through and we talk about the exemption for the 20 megawatts, this exemption here exists for a very clear reason. When we look at what share of biomass is being used in these large installations that are over 20 megawatts, we actually see that over 75% of the biomass that's being used is being captured by this regulation, so it is quite efficient. However, it's only impacting 12% of the actors, and this also happens to be in line with the emissions trading scheme. So therefore, it creates quite a lot of coherence across the different EU legislations. So that was the original justification for why that exemption was going to be in place. And then if you go to the next slide, looking forward and talking about the end use criteria, which I think is going to be important for quite a lot of the people listening today. Here we're talking about the greenhouse gas emission saving criteria. And so these criteria are different for operations starting at different times. So the first requirements for transport fuels, there was the requirement that all installations that were operating prior to the 5th of October 2015 would have a greenhouse gas emission savings criteria of 50% or greater. After that date, it would be increased to 60. And then starting in January 1st, 2021, it would be 65%. And for electricity, heating, and cooling producers, the first criteria came into place in 2021. And that was going to be to establish a savings of 70% or greater. And then all new installations going forward in 2026 will have to reach 80%, but that is only applying to new installations. Next. So when we're talking about these greenhouse gas savings values, there are two different ways to go through and to calculate this. You can either use the actual values or default values. And so when you go through and calculate this, essentially what it's looking at is, what kind of greenhouse gas emissions do you have from the extraction or the cultivation of these materials? Are you, going through and using fossil-powered equipment to go through and do that? When you are harvesting these materials and processing them, is that being done with fossil fuels? Do you have any, a gas boiler who's going through and drying the material to prepare it for processing? And then how is it being transported to where it's eventually going to be used? Is that, using biofuels? Is that using conventional fuels? And so all of the fossil fuels there along the supply chain are considered here. And that's where the savings need to come into place. The negative values you see there at the end are referring to carbon capture and storage and different ways to go through and reduce the greenhouse gas emissions, but we don't really see a whole lot of that uptake at the moment, but that's an area where we are expecting to see a lot of growth moving forward. If you go to the next slide. So talking a bit about the specific provisions for electricity-only installations, as Manolis was mentioning in his earlier presentation, one very important thing under the RED II is that you cannot have fossil fuels as the main fuel. The main fuel has to be biofuels. Otherwise, it's no longer eligible. And you also need to prove that there is no cost-effective potential to do highly efficient CHP. Otherwise, it is expected that you do that. So when we look at installations that are below 50 megawatts, here we don't have any specific requirements for the electricity-only installations. But once you get above 50 megawatts, then you begin to see special requirements being put into place. So for installations between 50 and 100 megawatts, here there's a requirement to adhere to the best available technologies and to have associated energy efficiency levels. So we're generally talking somewhere in the range of 32 to 38%. Or the installation is also able to use biomass CCS, in which case it is considered to meet the efficiency criteria. And then once you're talking about installations that are over 100 megawatts, there's not just the best available technology, but there actually is the electrical efficiency rate of 36 that is required for all installations, or they can also be operating with biomass CCS instead. Those are the two options that exist for them. If you go to the next slide. However, there have been a few challenges with the implementation of RED 2. There have been quite a few implementing acts that were expected from the Commission, such as the Operational Guideline on Forest Biomass and the recognition of voluntary schemes. Unfortunately, these have both been delayed and have still not yet been released, which has then resulted in an adjustment to the monitoring and reporting regulation for the emissions trading scheme. Initially, the way it was set up is that starting from January 1st, 2022, all member states would need to be going through and demonstrating the sustainability of biomass in order for that zero rating to be maintained in the ETS, for eligibility of support, and to count towards renewable energy targets, all of the things that I was talking about at the start of this presentation about why the sustainability criteria are so important. However, with this adjustment from the Commission, these criteria are going to be able to be considered fulfilled for the next year, while these voluntary schemes to verify this compliance are vetted and approved by the European Commission, and for these implementing acts to go forward to create the framework that's needed to operationalize RED 2. And then if you go ahead, I will now give a quick overview on what some of the changes we can expect in RED 3. So looking at the next slide, we see that there are a bunch of different proposals on the table here now. There's some discussions to lower the exemption threshold that we were talking about that's set at 20 megawatts down to 5 megawatts. So this would mean that a significant new portion of plants would need to adhere to these criteria and to demonstrate their compliance. There's been the discussion that subsidies for power-only installations for forest biomass would need to be ended by 2027. There are some proposed exemptions for installations that are operating with bio-CCS, or for installations that are in areas with a just transition plan. And then there's also the proposition that these retroactive application of greenhouse gas savings emission criteria that I was talking about, that these actually be made retroactive, and so that they apply to all plants, existing and new, not just the new plants as was previously required under RED 2. And then there are also additional requirements that are being proposed about limiting areas that biomass can be harvested from, new requirements for what kind of practices qualify as sustainable forest management, and additionally on creating a concrete regulation on the cascading use of forest biomass. So if you go to the next slide, we have a few general recommendations on a lot of these points. We think that this lowering of the exemption threshold could definitely be problematic because it could increase the regulatory burden on a lot of these small actors. As I mentioned, right now we have a very effective regulation in place that operates quite efficiently. But if we were to go through and extend it to a bunch of these other actors, then that could increase compliance costs, especially given the delays that we've seen coming from the Commission side in recognizing any of the voluntary schemes. Additionally, on top of that, we think that the retroactivity of the proposed greenhouse gas emission saving criteria could negatively impact the sector by undermining market stability and investor confidence. This could create a framework where biomass isn't considered as secure an investment moving forward. As Manolis was talking about, there are significant capital costs at the beginning, and so we see that this could be an area that could potentially create some challenges. And then also the institution into legislation of the cascading requirements could create a framework that ends up distorting the market by placing very strict criteria on what is able to be done and how different material needs to be processed, regardless of local factors and local conditions. So we think that those areas could cause some problems in the future. So I think I might be over my time now, but I'd like to thank you all for your attention. That's all I had for you today, and thank you.
Thank you very much, both Daniel and Zilis, for giving us a quite detailed overview of the situation both on the market and the policy side in Europe. And I would like to move forward to Marco Axelli, Development Director of EPH, in order to give us a presentation about what biomass utilization means for the company, past projects and possibly future ones. Marco, the floor is yours.
Thank you, Manolis. I'm sharing my screen. Can you just confirm that you see it?
We see it, but it's not yet in full screen mode.
How about now? It should be. It is on my screen.
Not here, no. Do you want me to share it instead?
Yeah, why don't you do that? Good, excellent. So thank you, Manolis, for all the good work and for inviting us. We are today one of the largest operator of biomass plants in Europe, and so I wanted to bring to the table our experience in the field. By the way, also congratulations to all the good job by Gilles and Daniel at Bioenergy Europe. We're working closely with them on particularly the regulatory side, which, as we will see, is particularly complex at this time. If you want to move to the next slide, today we are in the midst of an energy transition that has been coming at the intersection of three main forces. So the first one was regulation, particularly with the creation of a single market and liberalization of the energy sector. The second is technology. This was driven by these regulatory changes, particularly in solar and wind technology. And the third is the market fundamentals, where after the two big crises of 2008 and then most recently with COVID, the fall in demand has created some imbalances in supply and demand that forced a lot of historical legacy incumbents to rethink of their business model. And if you want to move to the next slide, that actually created a lot of opportunities for newcomers like EPH. EPH is a Czech group that was founded early in the 2000s and basically grew through acquisitions in this new world where all the legacy utilities wanted to divest the fossil fuel assets as they were moving into more renewable generation. So through subsequent acquisitions, first of regulated assets, when everybody was going merchant looking at increasing power prices. And then from 2013-14 onward, when everybody was concerned about the dynamics of the merchant power, we acquired a significant number of assets that today make us the sixth or seventh largest generator of electricity in Europe, with a business that generates about 2 billion euro in EBITDA and about 600 to 700 million of free cash flow every year. If you want to move to the next one, as we developed this portfolio, which was driven by the realization that it's not that we're a dirty player like some define us simply because we acquired a lot of fossil fuel assets. Our rationale and our thinking was that at that time, when everybody was saying by 2040, 40% of generation needs to be renewable, I don't think that a lot of people focused on the fact that in that case, still 60% had to be fossil. And if at that time, coal and gas-fired generation was not making money, something had to change, either the regulation or the market, and that happened. So we bought it. We bought these assets, but at the same time, as we were buying these assets, we said, but in reality, even when 40% of generation is renewable, what we will be missing in that architecture is dispatchable renewables. And in particular, we focused on energy from waste, biomass, biogas, biomethane, anything that is programmable and can be a complement. And as we were saying before, kind of like the stable anchor in the energy complex that we were building. And so we focus particularly on biomass and solid biomass, which is more complex than wind and solar. So it requires more industrial knowledge to own and operate the plants, but at the same time has a significant scale, unlike liquid biomass and gaseous biomass, to really contribute to the stabilization of the electricity sector in Europe. And basically what we did, we bought another 80 megawatt of power generation for a total of 600 gigawatt hour, investing over 200 million euros, which gave us also access to direct knowledge of the commercial side, particularly the biomass sourcing. If we can move on to the next slide, the complement of this is basically this opportunity that we spotted in this industry transition. So the first realization is that sites are limited and increasingly difficult to develop, so we should valorize them. So when we buy fossil fuel, we know that at some point they will finish their life, but we can use them to do something else. The second point is exactly that fossil plants will be retired over time, but are still needed over the next 30 years. So we have some time to basically develop this transition. And the third point is that assets can be managed responsibly to create more opportunities. So good ESG practices require managing assets, not just selling them. A lot of the companies, a lot of the utilities that proclaim themselves as really decarbonizing, in the end, what they did is they sold their power plants, while what we do is we take them on, we reconvert, we mothball, or we shut down responsibly, so that basically today, 80% of our EBITDA comes from CO2-free assets and 15% from low CO2, which is basically gas. So only 5% of our EBITDA today comes from, still comes from coal, and we have set a goal to reduce CO2 emission by 60% by 2030 and zero coal by 2030 outside of Germany, where basically there is an agreement for phase out that goes all the way to 2038. So that's what we think is managing the assets responsibly in terms of decarbonization and phasing out of coal. If we can move to the next slide, this is what a brief summary of what we have done so far and what we are doing. So the first one is reconversions, and we are reconverting or have reconverted over 2,000 megawatt at Linemouth, where we will spend some words on it, and two power plants, South Amberbank and Jenswald in Germany, that were reconverted to energy from waste. And the second is over 5,000 megawatt that were put in coal reserve or decommission, which altogether contributed to 12% of the total CO2 reduction in Europe in the period 2014 to 2018. Next one, please. On top of that, what we're doing is we are also investing in new renewables and converting existing plants into something that is more efficient. So our existing gas-fired generation is also being reconverted to higher efficiency, basically from the high 40s and low 50% efficiency to the current 60% and more efficiency in the age technology. We invested over 1 billion in the last 5 years, and 1 billion will be invested in the next 3 to basically bring this decarbonization plan over the next decade. Next one, please. Which brings us to basically our direct experience in biomass and the reconversion, which is at the core of what Manolis was describing before. Linemouth is the first project. It's a project that came into operation as a coal-fired plant for an aluminum smelter in 1972. In 2014, the plant was awarded an investment contract from the UK government to reconvert from coal to biomass through an extensive capex plan of over £300 million. In 2015, this investment contract received the state aid approval. So you saw that basically took more than 2 years between regulatory and permitting to then start construction in January 2016, which was then completed in just over 2 years. securing 420 megawatt gross renewable generation that will be running until March 2027. Next one, please. This is the largest one of the largest with Drax plants that were converted in the EU at the time and in the UK, with 420 megawatt gross and 390 net capacity exported to the grid, saving approximately 1.5 million tons of CO2 emissions compared to the previous coal operation, with an investment that basically tackled both the power plant and the biomass storage capacity, both at the Port of Tyne for 75,000 tons and 50,000 tons at the stations, plus all the logistics of 1.8 million tons of pellets that are coming mainly from Canada and the USA through the direct sea rail infrastructure network that basically links the port to the power plant station. And that is maintaining basically all the 150 jobs that we had at the power plant before converting it. That is another big claim that we make about biomass as a secure renewable energy in the sustainable architecture that the EU is developing. The fact that we can support a similar level of employment that we had also with the power generation from coal, as opposed to wind, solar, and battery storage or other technologies that are really low employment. If we move to the next one, we move to the other projects. So the first one, Linemouth, is completed. It's running well, and we're very happy with that. And so we said, why can't we replicate it in other power plants in our portfolio? And the choice fell onto Fiumesanto, which is a 600 megawatt coal plant in Sardinia, in northern Sardinia, with a reliability must-run contract until the end of 2024, so basically 2025, and a planned coal phase-out thereafter. So it's one of the two plants on the island where the system operator certified that there is a need for 600 megawatt of baseload capacity on the island to guarantee system reliability. So we took it responsibly and said, well, we have an idea, we would like to convert it to biomass because that's the fastest way that you can convert it between permitting and the actual physical work at the plant. However, there is also a strong lobby, let me say, to bring gas to the island. Today, there is no significant gas demand. And so there is a big gas project to build a main line, a trunk line from the north to the south, and basically change the LPG gas that is used today to methane. So we said, of course, we can also look at that solution, but it will take longer. And from a regulatory perspective, we need somebody who guarantees that by the time we do the reconversion, the gas will be there. So we think that from a regulatory standpoint, it's a little more complicated, but still doable. And then there is a third option, which is being promoted by Enel, which is the largest operator in Europe, so the incumbent utility, who says, actually, we can do everything through solar PV and wind plus battery storage. So you have these three projects or these three solutions that are kind of fighting each other from a regulatory standpoint, because, of course, each one at a different level needs some kind of regulatory framework to be developed. The project that we started together with the Center for Renewable and Technology and BEST and BTG is a 150 million euro investment that highlighted no significant technical, operational, or commercial red flag. So we could start construction, permitting and construction tomorrow. We expect about 18 months for permitting. It could be accelerated maybe to 12 months and about 24 months or potentially up to 30, considering a very conservative schedule of EPC construction. So basically, it's a project that could be done in 3 to 4 years. So if we start to work now, we can come exactly in line with the government target of phase out by 2025, which is something that you cannot do purely with renewables or with the gas conversion. But there is a support scheme that is needed. The support scheme needs to be introduced by the Minister of Energy Transition, and it has to take into consideration both the implication of RED II, which are mainly the minimum efficiency program that was described before, which is mainly the 36% efficiency, which we saw from the technical feasibility study that is achievable. And now the RED III implications that Gilles and Daniel were describing. So no new support to power-only plants after 2026. And here, considering that it's a warm climate and there is no industrial activity, in fact, it's an area of what they call complex industrial crisis, meaning that there is a lot of unemployment, up to 40%. There is not even a need for local cogeneration for industrial application. And the third one is the political support. So we have a lot of support at the local level from the mayor, from the region, from the unions, but we don't see as much support in the European Union and the central government. If you go to the next slide, we see a little bit oversight of how simple this conversion would be. So we can keep the steam turbine and the generator, we can keep the ESP, the electrostatic precipitator, and we will only need to do some conversion to the mills, to the boiler, and to the flue gas treatment system, which is very limited in our mind. And if you go to the next one, is mainly on the fuel handling, where both on the ship offloading, the coal tower, and the new biomass silos and internal conveyor system that will bring it from the silos to Unit 4 of the power plant that would be reconverted. It's all together, you know, some, from a technology standpoint, very simple activities that we can do, and commercially quite simple also because we can source the pellet from the general market. Next, please. It's basically the summary of the issues that we see for the future conversion. On the left-hand side, you see the benefits. So it's the reduction of the CO2 emission that is 70 to 80%, so fully compliant with RED II and RED III versus the fossil alternative. It's also reducing methane emissions because the wood left to degrade in the wood where the pellets are produced, and sometimes, oftentimes, actually, it's the byproduct of industrial production, would have 85 times effect of the CO2 that is avoided. The next one is the baseload production that provides up to 25 euro per megawatt hour estimated reduction in grid and system cost. The next benefit is the lower use of land. So if a Fiume Santo conversion had to go full solar panels, we would need 50 square kilometers of new land occupied by solar panels. We would also bring a reduction of hydrogeological and wildfire risk. And here there was a recent study that showed that Italy, in the last 5 years alone, added 5% of forest land, but 14% of wood mass and 69% of dead wood since 2015. This is what, under heavy floods or in the summer, basically causes floods and wildfires. And if you could use it, and we assume that about 10% to 15% of the total generation of the power plant could come from local production, would also significantly reduce and have a very high network, positive network externality in reducing hydrogeological and wildfire risk. And the last one is the large employment that we saw. However, the challenges were already described. Today, biomass is not always seen as green by some NGOs and some political parties. There is an increase in support to hydrogen and battery storage, which is seen as an alternative as a solution. And the RED III proposes no new support to the power-only biomass after 2026. So if we move to the next slide, we see the conclusion that is basically, unless we act together and we convince the European Union to tweak RED III and the related local regulation to enable power-only generation, or at least to have the exclusion that if you cannot do cogeneration locally because it's a warm weather or there is no industrial activity that justifies the use of cogeneration, we see that coal to biomass conversions and new biomass plants in Europe probably will not have a future in the European Union. So I think that this is a call to everybody to speak up at the European level so that we can support this type of projects also in the future. Thank you.
Many thanks for the excellent presentation, Marco. I hope you will stay for us until the end if you have any questions, audience.
Yeah.
But without further ado, I would like then to pass the floor to our colleague Anes Kazadzic from Elektroprivreda, Bosnia and Herzegovina, also working in the Biofit project, to present some main conclusions and activities in Bosnia, also related to Biofit. Anes, the floor is yours.
Do you see my screen, Manuel?
No.
Mm-hmm. And now?
Now, yes, but please go into full screen mode if possible. Perfect. Okay.
Super. Thank you, Manolis, for this introduction. Also, I would like to thank you, BGT, as a coordinator of the Biofit Horizon 2020 project for the organization of this Biofit industry session. And thank you for inviting me to say something about our activities, plans, and concrete case studies for our projects within the Biofit study. My name is Anes Kazagic. I come from EPBIH Power Utility of Bosnia and Herzegovina. I'm working for Strategic Development Department. I'm actually head of the department. And on behalf of our team, I'm going to say a few words about this topic, decarbonizing our power utility through biomass retrofitting at our two power stations, Tuzla and Kakan. So first, few words about present generation technological mix of our power utility. Our generation of power and heat is based on production in two large coal-based power plants placed in Tuzla and Kakan, then three large hydro power plants, six small hydropower plants, one wind power park. So our annual power generation is 7,500 gigawatts hour a year, and we also produce 350 gigawatt hour of heat on annual basis, and deliver the heat from our cogeneration power plants to the three cities in Bosnia and Herzegovina. Installed capacity of fossils versus renewable energy sources is at the moment two-thirds in favor of fossils. So we are in a process of energy transition to the renewable energy sources. Some of key energy indicators of the company, we burn about 5 million tons of coal a year. Average net efficiency of our thermal power plants, not accounting cogeneration mode, then only condensing mode, is 31. Annual CO2 emissions is 5 million tons a year. Some average CO2 emission factor from our thermal power stations is 1,000 kilogram of CO2 per megawatt hour, while average net emission rate, including renewable energy power from renewable energy accepted from some smaller qualified producers is about 670 kilograms of CO2 per megawatt hour. I will not say anything new if I say that we have our targets for decarbonization until 2050. So our previous targets for reduction of CO2 to 2030 was 30%. That will be adjusted by a new figure from National Energy and Climate Plan, which will be some above 30%. It is expected to be published in March this year. For 2040, the target is 55% cut, and to 2050 at least 80 or near 100% CO2 cut. Three key measures to achieve those targets: increase of renewable energy sources, increase net efficiency of our thermal power stations, and as a third pillar of the measures is biofuels use instead of coal in our power plants. So in some basic scenario, this is transformation of our technological mix until 2050, where we can see some trend of transformation from the dominant fossil production to the dominant renewable energy sources until 2050. When we talk about roadmaps, we are already in energy transition. Decarbonization is in the beginning phase of discussion in Bosnia and Herzegovina. It will be the latest 2050, but there are also some talks about some earlier year. What is very important for us is a just transition of coal regions in Bosnia and Herzegovina. So we have a program of transition of our coal regions with decreasing of people employed in the coal mines, with decreasing of coal production and supply to our power plants, and the development of some green jobs on our coal mines, which is at the moment related to the installation of photovoltaic power plants and also bioenergy crops plantations. So as our commitment is, I can finish this part of presentation, that bioenergy, that we see the bioenergy as a part of solution for decarbonization of our generation portfolio. So I will say now some about our previous, ongoing, and future bioenergy activities. When we talk about bioenergy activities, we first need to start from the logistics and the types of the biomass that are to be used in our power plants. So we started first from waste woody biomass option. Then we continue our activities with short rotation copies and other bioenergy crops plantations. And also in some recent time, we started some activities to the development and implementation of the waste to energy options, meaning introducing of some fuels from the waste in combination with other fuels for our power plants. We also 15 years ago started with the research into possibilities of co-firing, biomass co-firing in our power plants. So we actually investigated the different combination of use of our coals with different types of biomass, waste woody biomass, and also bioenergy crops in different ratios. We first started that on lab scale facilities, and then 5 years later we started with first biomass co-firing trial run in our power plant, large power plant Kakan, where we started to use 5 to 7% of waste woody biomass in combination with the coal without any adaptation on the equipment on the unit. So it is actually simple mixing of the waste woody biomass, chips and sawdust with the coal on the coal depot, and then transportation by belt conveyors to the coal bunkers and introducing through the milling burner line into the boiler. We notified a list of synergy effects of use of this type of biomass in combination with the coal. The coal that we use is a low-run coal, so wooden biomass even improve the characteristic of the fuel in our power plant. Then in 2020, last year, we, after detailed analysis, we started with the plantation of the bioenergy crops on a former land of some of our coal mines. So we already established some experimental test plantations, and we now supervise the growth of the plants, and we are going this year to multiply these test plantations by 15 new hectares of plantations of willow. This is the type of short rotation copies that we planted so far, and we have a possibility to actually establish more than 1,000 hectares of the former land of our coal mines with these plantations, and to use our own grown biomass for biomass coal firing in our power plants. And as I said, we also started with some research into use of the RDF in combination of the coal and the biomass for use in our coal-based power plants, and we have a program of implementation of this project for our 2 power units in Tuzla and Kakan. And finally, we come up to the Biofit studies. Within the Biofit project, we had opportunity to offer and to investigate 2 our case studies. One is in Tuzla power plant on unit 6, a cogeneration unit of 2020, actually 223 megawatts of electric and 220 megawatts of thermal or heat in cogeneration mode from this unit, which will use 15% of the biomass in operation. And the second project is full biomass repowering of unit 5 in combined heated power Kakan station. So we first started with the target of 0.3 biomass co-firing on unit 6, but we established together with the CERT and Manolis team the calculation for transformation of the combustion for the biomass co-firing at average 0.15 biomass co-firing, where we would use different biomass types as waste wood, agricultural biomass, and energy crops. The second project in Kakan power station consider full biomass conversion, where we would use waste wood at 90%, while rest of 10% would be difficult or hard to manage fuels as energy crops, RDF, or even coal. So this unit 6, we modernized this unit in 2013, increased the net efficiency of the unit. We have 2 rows of 12 burners, low NOx burners, and OFA systems installed. and the coal that is used on these units is of lower heating value between 14 and 16 megajoule per kilogram. We consider to use the biomass co-firing through the dedicated biomass mills and biomass burner that will be installed on the existing boiler of Unit 6, and of course the storage system would be installed near the coal depot of this unit. So some of the next steps for this unit, further investigation of the logistics for the collection of the necessary amounts of the biomass, which will be in the range between 6 and 14 megajoules per kilogram. And we already started with a trial run of biomass co-firing on this unit. At the end of last year, we started with 10% of biomass co-firing, and preliminary results are very good. We have no any problems with co-firing of 10% of biomass on this unit without any modification of the equipment, and we will continue this trial run this month. And also because the Biofit study for Tuzla Unit 6 in final stage of completion, we plan to finish this study. I think Manolis can confirm until end of this year or beginning of the next month, end of this month or in the beginning of the next month. And the capex that is estimated in the study and that is necessary for providing continuous biomass co-firing of 15% is about 10 million euros. When we talk about this Unit 5 in Kakan power station, it is specific combustion system installed on this unit. It is actually slack tap boiler furnace with some increased temperature in the furnace, but this unit is also modernized, and we have installed also 12 low NOx coal burners placed in 2 rows of a system. Boiler efficiency is very high for this type of the unit. LP and high pressure turbine modernized, hybrid ESP buggy dust filter enable PM emission below 10 milligrams per normal cubic meter. And we use a so-called brown coal on this unit. And this unit is actually envisaged for opt-out. It can operate until end of 2023 on coal, and then we need to actually adjust it to industrial emission directive or to replace the fuel on this unit. That's why we started this project. What is envisaged within this project is a replacement of the furnace with bubbling fluidized bed furnace, and estimated capex is about 30 million euros. And we also started with a trial run on this unit with the possibility to test 10, 20, and 30% of biomass in the fuel mix for this unit. This process is in preparation, and we plan to finish this trial run until end of March. And I hope we will have Manolis, you on site when we run these tests in Kakan power station. So to conclude with some list of benefits of launching these 2 projects. These 2 projects will significantly actually reduce CO2 emissions from power station of Elektroprivreda. Both projects are cost beneficial. That's a preliminary result. We will see the final result soon. Pollutant emissions are further decreased. We also have some trends of electricity price and as price which actually play in favor of launching these two projects. And there is a compliance of both projects with greenhouse gas criteria from RED II. When we talk about some challenges and risks, I should emphasize that insufficient biomass quantities that can be mobilized to ensure the operation on the units can be a sort of a real challenge. Then we have through risks from a regulatory point of view related to RED II, where actually we couldn't recognize that biomass co-firing is recognized as renewable energy in RED II, because the biomass in case of Tuzla 6 is not actually the main fuel. For Kakan unit 5, it is different situation. We can recognize that it is renewable project from RED II because we have a full repowering by biomass. Then what we can see that the minimum net efficiency that is required by RED II is 36 net efficiency, while we have a bit lower net efficiency both on unit 6 and unit 5. So we need either to ask for some sort of derogation in Bosnian RED II, or to launch the project of replacement or some further modernization of the turbine set to achieve net efficiency of 36%. And finally, what is very important to emphasize and to discuss maybe on the level of the project of Bioenergy Association is that the RED II doesn't recognize the cogeneration on a large power heat and power stations as a socially and environmentally beneficial. Then only recognize high efficiency cogeneration as a beneficial. We have a situation that from those two units we have a delivery the heat to the more than 200,000 people that are living in Tuzla, Lukavac and Kakan, plus delivery of the heat from cogeneration from those two units to the industry in those three cities, and we actually cannot be supported by RED II definitions for such projects. Thank you for your attention.
Many thanks, Hannes, for this clear picture of your activities. Before continuing, I would just like to ask Doris, what is the plan? Because we're a little out of schedule. So what time do we have to finish?
Yeah, it would be great if we could start the discussion now. And if, I mean, best case would be we finish discussion at 3 and start with the next industry session at 3:15. But yeah, that's at least the plan. But I think we could start with Q&A. I've seen at the chat there are already some questions answered.
I think we've addressed most of the questions in the chat. Maybe I can ask, apart from Hannes, also Zils and Marco to turn on the cameras in case there are any questions. I think anybody from the audience can also take the floor and ask any questions they want just by opening up their microphone. So if there's anybody who wants to do that, then they are free to do so. If not, maybe I can ask a few questions, as is typical in such cases. And maybe I will start with Marco. Marco, you presented a few cases about energy to waste plants that you are also working on as a company. Do you see a lot more future in that when it comes to converting coal power stations? And if yes, what could be limitations? So I hear that a lot about that in Greece, for example, as a possible future for the coal plants, but I'm not fully convinced that the RDF supply, for example, exists to allow a big conversion project to take place?
Yeah, I think, well, one of the plants we're converting is actually both are very large. So at the end, you're simply using the same site. Sometimes you install almost like a full new plant, because you're moving from 1,000 megawatt to 50 megawatts sometime of electric capacity. So I think the potential is huge. Basically, all the coal plants have the potential for that. The big issue is the local acceptance, which is very difficult in all Southern Europe, which is where we have a problem of what to do with the waste. In Northern Europe, the problem is quite the opposite. The problem is a lack of waste, even for the existing waste plants. If you look at the Netherlands, Germany, particularly. So I think, one is local acceptance and the other one is availability of waste.
And one more thing for you about Sardinia. Can you confirm that it's not possible to support the Fiume Sando project because the area is not recognized as a region with a just transition plan?
Yeah, unfortunately, it was not put into the list. So it is, and we're working also with Bioenergy Europe on the amendments. It is not a just transition, but it's an area of, it's called European cohesion. So the fact is you have 40% unemployment rate and the power plant there probably is, I don't know, 20% of all the industrial activity. So it is a significant employer. And so again, it's too late to consider it a just transition, but if we could make exemptions to call it also to include also the area of European cohesion, that would be helpful, potentially.
Of course. Thank you, Marco. I see a question from Rainer.
Yeah, many thanks to all speakers. That was really very enjoyable to listen. My question would be to Marco. In your presentation, you did address the topic of locally sourced biomass, however, not very much in detail. Now, obviously, when talking about local acceptance and all these sustainability issues, a lot of people are criticizing imports from US and Canada. Not so much in this call, I assume, but complementing by locally sourced biomass could maybe bring some additional arguments, including job creation, value creation, all that.
Precisely. So the study that we developed also looked at how much could be sourced locally in Sardinia, and we estimated about 100,000 tons, maybe 150. But the total consumption of a plant this big is, probably 1 million ton or thereabout. So you're looking at 10 to 15%, and the rest, the natural supplier is North America at the end of the day. In general, Italy, as I showed, it doesn't use a lot of the green gold, that we have, because only, I think, 35% of the natural growth from Italian forest is harvested for industrial and energy uses. So it could be pushed more. But one of the issues is economics, because Italy has a lot of mountains. And so at the end, it still might be cheaper to bring it across, the ocean than to source it locally. So it should be maximized, but the potential is more or less that.
Thank you very much, Marco.
I see there is a hand raised from someone in the audience. So if you can please, unmute yourself, state who you are.
Yeah, my name is Jan van den Aweren, working for the company Engie. I was wondering, and it's a question to the entire panels. It's been highlighted very, very quickly, I think, in the first presentation regarding the pre-treatment of biomass. Yeah, I think we all know today they are looking at torrefaction, at the steam explosion. We're also talking about today about HTC, so hydrothermal carbonization. Because most of the power plants, they are based on rather clean wood, let's say. So it is a rather easy fuel. But those more difficult fuels, there we need to pre-treat them before we can use them in, let's say, the the high steam parameter boilers. What is the experience of all those pre-treatment systems up till now, by your knowledge?
Who would like to start first on the?
I can say that we investigated that, but you know, it really adds value for new reconversion. So for line mouth that is already converted, the big value of you know, steam process is that the conversion is much cheaper, but now it's done there, and so the fuel is probably a little more expensive. So then we shifted to Fiume Santo, and we did some preliminary investigation, but then we stopped. Because basically now all the activity there is on hold until it is clarified whether the project from a regulatory standpoint can happen.
Hannes, you want to add something because you have some experience?
What I can say from our experience is that we had an idea of our flame from Norway to develop together the project of black pelleting in Bosnia and use of that product black pellets for our power plants. You know, we have a lot of locally waste wood biomass, and we also have a good developed production of the pellets that are not only used locally, then also exported in the Italy, Slovenia, Croatia, and Austria. And the Norway company Arbaflame, which also developed the only one project in Canada, tried to develop this project together with us. But unfortunately, we together found that it is not feasible in our case, that it is much feasible actually to use locally sourced wood chips and sawdust, and our projects based on that type of biomass.
Yes, okay. Maybe I can add, because myself, I was personally involved in the Arba Heat project. Maybe some of you have heard of it. So it was a retrofit of the power plant in Rotterdam to black pellets coming from Arba Flame. But because I'm working for Laborlec, which is a research center, yes, and I'm personally also very interested in the potential of, let's say, more wet biomass streams, waste wet biomass streams, let's call it like that. And it seems to be that there maybe HTC, hydrothermal carbonization, could offer a solution. I'm just saying could, but because in my understanding, there is still a bit of lack of experience. I'm not sure if one of you already have heard of that process or have studied it, or
Personally, I can say I'm aware of the process, but from what I understand, also it's still not deployed on a commercial scale. So it has the situation of, I think, the typical chicken and egg situation we are facing in these types of new projects. And to some extent, the same goes for torrefaction, for example, which
yes.
I would say more mature technology. On the one hand, you see that utilities are a bit skeptical about such an option because they consider the market is not yet mature. On the other hand, all the different policy implications have kind of put a stop to conversion projects, and this in turn, I would say, stops developments in the market development if it targets the power sector. Lately, I think that what we have seen is that there is an increased interest in the use of thermally treated biomass, mostly I would say in the industrial sector, in the energy intensive industry sector rather than the power and heat sector. We have actually another project, sister project of Biofit called Music, that is working on those issues. And I would also add that I think when it comes to the power and the power sector, perhaps an idea for such kind of streams would be to use them only for peaking capacity. use them only in smaller quantities for plants that are providing peak demand whenever it is required. But again, all the policy hurdles we have discussed, either under RED 2 or under RED 3, can be an issue for deployment. But that's my perspective.
Yeah, sorry, but you mentioned at a certain point that there is a project going on studying these things. It was 3. I did it.
Music. I will write it in the chat.
All right. Thank you. Okay. Thank you very much.
Zils, you want also to add something maybe a bit about the market's perspectives, either of wood or black pellets?
Yeah, I can only say a few words indeed on the steam explosion and on the torrefaction, maybe even more on the torrefaction. We see that we're getting to an industrial scale, because now there are indeed some projects that are about to produce industrial volumes, or that are currently producing industrial volumes. But I guess it would be lying saying that it is a mature market. The only thing that I've noticed is that, at least for the torrefaction, I have the feeling that indeed, except for a few Asian prospects, I have the feeling that the market is going more and more on the non-energetic use of the torrefied product rather than energetic use of it. So maybe there will be somehow a shift in that market.
Right. Thank you.
Thank you, Zil. Okay, I know the project is about biomass, but I think when it comes to discussing the power sector now, it's almost unavoidable to slip into the issue of the natural gas use and its implications. So here another question about to our speakers is, I think also you, Marco, you mentioned that you see natural gas as a possible alternative for Fiume Santo. You think that's, let's say, something that can happen more easily than a biomass conversion?
Yes, because it looks like the government is supporting it more. So since at the end you need the government support, it is more likely. I think in general, there is a lot of geopolitical in playing right now. So I don't think that these gas prices will be sustained for a long time. Although it is true that we're managing the whole energy transition poorly, too much emotionally. And so oil and gas companies cannot invest in their core business as much as they could in the past. Banks
Marco, I think we are losing you, folks. Marco Zimas is frozen, unlike the gas prices. Maybe until Marco is back on the line. Anes, what is your Bosnian perspective on this? Do you see a future for biomass in the Bosnian power? Of course, you see as a power mix, but with expanding natural gas, do you see a competition perhaps that could push biomass out of the market?
What we have actually in Bosnia is some kind of the discussion about replacement fuels for the coal on our power plants. One pillar is biofuels, including waste, but there are also some voices that suggest gas as a replacing fuel. What we have in our company is one developed project of CCGT unit in Kakan site, about 200 megawatts, 120 electrical and 80 megawatts of heat on CCGT unit, which will be supplied with gas which comes from Russia. That's actually the big issue for launching that project. We will see what will be with this South Pipe project. If it is be a reality, then probably that project for Kharkiv site will be more in focus. So I will not say that there is a competition. I even can say that there are enough space both for biomass and gas. But I wonder if launching the gas projects now are a clever idea, not only because of a supply issue, and also because of the climate targets issue in the future, let's say behind 2030 and 2040. I think that the gas will be also target as the goal is today.
Thank you, Hannes. Maybe I can go back to Marco because at some point we lost you. So just.
No, as I was saying, so one is government support. The other one, in terms of cost, I don't believe that these high levels will remain, for a long time. But at the same time, the fact that we're managing the energy transition very emotionally is cutting exploration and production activity, and so it will be higher than what we have experienced in the past. But I think if I were to speculate, the power price of 60 euros or something should be the normal level, 60 to 70 euros. And so that is still cheaper than biomass. And so we need a regulatory support if we want new power plants.
Thank you. And for the conversion project for gas, are you considering retrofits in the existing units, or is it like a totally new one? Okay.
Yeah.
Thank you. Okay, I don't know if there is any other question, or I don't see any more. It's the chat, and I think we have to stop anyway to have a short coffee break before the next session starts. So first of all, I would like to thank all the speakers, both for their presentations today, as well as for the continued support during the project implementation. We have been working on some of those case studies now, I think, for well, not from the start of the project, but I think almost 2 years now. And we had also the very good support from Bioenergy Europe in all policy issues. One last maybe a question from Jan again.
Yeah, my apologies. These presentations, they will be shared, I suppose?
If the speakers agree, I think they will be uploaded on the site of the project.
Yes.
Fine.
Okay. All right, thanks.
Perfect. Okay, and I saw already that to answer your question that about the hydrothermal carbonization, that in the chat there is a link with a paper from Bioenergy, and also there's going to be a presentation tomorrow at the industry session related to the pulp and paper session. So that's a very good, I think, incentive for those of you who want to learn more about the different technologies to join those other sessions as well. And about the final policy recommendations, also we will have the policy breakfast that Patrick mentioned on Thursday morning. So it's another invitation for you to join. So again, thanks to all the speakers, thanks to the audience. And now I think we can stop for a break until the next session in about 10 minutes.
Thank you.
Thank you.
Good afternoon, everybody, and welcome again to the BioFit final conference. Can I hear something from Doris that I'm hearable?
You're perfectly hearable.
Thank you very much. Thank you very much. Yes, welcome back to the second industry session of the BioFit final conference on the refineries. I'll start by sharing my screen. This session is about co-processing in refineries, options, and experiences. We have several speakers, but first I would like to give a very short introduction on the subject. Fossil refineries, they're large industrial complexes producing transport fuels and other products from crude oil. There are about 94 refineries in Europe producing around 13% of the world refining capacity, which is still quite a lot. Here you see a very nice picture of a refinery of the Hellenic Petroleum oil company, which is part of the BioFit project. And of course, also for transport fuels, decarbonization is a necessity. And yeah, it's one of the sectors which is considered to be difficult to decarbonize. But you see now more and more strides are being made into that. European refineries themselves see the need for a transition. They have published a document for that, the Vision 250, and also a roadmap, which is called Clean Fuels for All. Bioenergy retrofitting is one of the techniques for decarbonization. CCS, CCU, and renewable hydrogen are other options. And yeah, there's quite a lot of interest in producing renewable fuels in refineries. The developments are going rapidly, not only in Europe, but also worldwide. Very recently, there was an article in Bioenergy International, which was called The Great Renewable Fuel Build-Up. A lot of activity is going on and a lot of interest is there across the industry. We're talking about co-processing of renewable fuels, renewable biomass to produce renewable fuels. Here you see a very schematic view of a refinery. A real refinery, people will gasp a bit, but for us, it is this is quite sufficient. If you have a refinery where you put in crude oil, you distillate it, and you get various products which you upgrade, you blend them, and you get various fuel products, and also fuel products. You can put in vegetable oils and then hydrotreat them and get fuels with biocomponents, or you can put in pyrolysis oil, which you can also use to make renewable fuels from it. Especially production of hydrogenated vegetable oils and HEFA for sustainable aviation fuels is happening now. This is a list of all the plants in Europe that are doing it. And I know that at the moment, as I present it, it's already outdated because developments are going fast. 4.5 million capacities, million tons per year is planned. In total, in the world, we're talking about, I think, 5 times as much in the next 5 years. So it's going quite fast, especially for HVO and HEFA. For the other option that we're discussing, that's pyrolysis oil. There, the first full-scale project is set to start with the pyrolysis plant of Preem. The Pyrocell pyrolysis plant in Sweden has come online lately, very recently, and the pyrolysis oil will be used in the Lysenkiel refinery of Preem. What will we do in our little bit more than 1.5 hour? We have 3 speakers. We have from NREL, Mr. Michael Talmadge has written an article on techno-economic analysis of co-processing of fast pyrolysis oil. We're very happy that he will be here and that he can present his work. We will also present the work of the 2 case studies. The first one is the integration of HVO production in the Thessaloniki refinery of Hellenic Petroleum. Evantia Nanaki and Dimitris Kourkompas will present this. And we have done a study on pyrolysis co-feeding of green transport fuels in one of the Total Energies refineries. After that, depending on the time, we will discuss recommendation and have a discussion and Q&A. I don't think it's good if I take more of the little limited time that we have. And I would like to ask Michael Talmadge to start with his presentation. Michael, are you there?
I am here, yes.
Hello, Michael. Very good to see you in live, in person.
Good morning, Patrick, and everyone online here. Thank you for having me.
Okay, I'll stop sharing so you can get the floor.
Sounds good. And let me just make sure I'm sharing appropriately here. Presentation mode. Okay, are we seeing my screen yet?
Yes, we can see.
Okay, great. I'll keep my camera on for my quick introduction, and then I will likely turn it off for the sake of connectivity. And hopefully my stream continues to come through as well. If I start to break up, please just let me know, and I'll try to find a different network. But my name is Mike Talmadge. I appreciate the introduction there, Patrick. I'm representing a whole bunch of people, both at NREL and our partners, Petrobras, in this presentation. And again, with that, I'm going to turn my camera off. So does everybody still have me?
Yes.
Perfect. Okay. So I'm excited to talk today about some work that NREL and Petrobras had completed on techno-economic analysis for co-processing of fast pyrolysis oil in fossil refineries. And this presentation will focus on the fluid catalytic cracking unit as an insertion point, fully realizing that we have a lot of industry emphasis on hydroprocessing. This project began about 7 years ago or so at this point, and really focused on the FCC as an opportunistic insertion point at the time, because that is a moving bed and has a pretty simple setup for catalyst maintenance and makeup and purge and all of that goes with this unit design, whereas the hydroprocessing unit is, of course, mainly fixed bed technologies. So just a little bit of background as to why the FCC was the focal point at that particular time. Okay, my quick agenda is just a very brief intro to the National Renewable Energy Laboratory, that is my employer, an overview of the refinery analysis that we have historically completed at NREL, and certainly the focal point of this presentation will be the results of the NREL Petrobras analysis. I'll talk a little bit about some new analysis and a little bit about some new analysis capabilities and various applications for it, and then I'll save time hopefully for some questions and discussion at the end. Okay, I'm going to keep close watch on my time as well. So the National Renewable Energy Laboratory, NREL, which is located in Golden, Colorado in the US, really focuses on advancing the science and engineering around a lot of different pillars in the renewable energy mix. So with focus on renewable power, improving energy efficiency across manufacturing and building technologies, really kind of optimizing our energy integration in the grid, bioenergy, and this is where I live, and that's why the bioenergy is bolded. And then NREL has a lot of these cross-cutting science areas that really cross all of these areas of research. So I'm going to pretend like I'm clicking on bioenergy here, and everybody can certainly go to nrel.gov for additional information. And I'm going to kind of drill down into the focus areas for today. So the National Bioenergy Center, or the NBC, is the location within NREL, or the area of expertise within NREL that really focuses on converting biomass to useful liquid fuels. And so this is kind of an extensive list of the areas in which we work. But let's see, I'm mainly focused in thermochemical processing, as you might expect, as we're producing bio-oils through pyrolysis and hydrothermal liquefaction, and then seeking integration opportunities with existing infrastructure. And that's kind of where I come in. And then I do have this cross-cutting techno-economic sustainability and market analysis pillar that my group is essentially supporting to enable the science and technology development in these areas. Okay, and that's our website, nrel.gov, bioenergy. Okay, so the purpose of our refinery analysis at NREL is to really look at two sides of this coin. And first, to leverage all of the existing refining and processing infrastructure that's out there. So if we're just looking at the FCC, 220 billion gallons is the number that we had last updated here, and that's certainly a lot of volume when we're considering in the U.S. context numbers like 35 billion gallons of SAF and things like that. So just to put in context how much refining capacity is out there, and we're really trying to utilize that to reduce the cost of biofuels. What we're really trying to do with refinery impact analysis, however, is complement the core techno-economic analysis that we're doing on converting biomass to liquid fuels. And so what we're really trying to do there is quantify the production cost. What we're trying to do over here on the refinery impact analysis side is see things from the refiner's perspective and really value the liquid intermediate propositions that are kind of being offered by the emerging biomass conversion technologies. So our focus here is really understanding the value of these materials. Then what we have is kind of a difference. So if the difference between the value that the refiner would pay for this product and what it costs to produce it is simply the profit opportunity, right? So it's important. We think it's important to understand both. Okay, what does it take to make things from the biomass, but what are they worth as well? And of course, that break-even value, we call that BEV, break-even value, represents the maximum price that a refiner would pay for this feedstock, right? And that's really a function of crude market prices, right? Crude and its derivatives. What are the demands of the various products that can be derived from these intermediates? What configurations these refineries have? Like, you know, a very complex refinery is very likely to have a different value assessment for these feedstocks relative to a simple one. Certainly the bio-oil properties. Okay, so this is really the space that we're trying to fill by working in refinery analysis. Okay, just a quick history of refinery analysis. So the National Advanced Biofuels Consortium was something that our group and NREL participated fairly actively starting around 2010. And from an analysis standpoint, we were just really kind of scratched the surface here, getting into looking at some of these bio intermediates that were offered by pyrolysis and hydrothermal liquefaction, and beginning to do some property comparisons between those and fossil-derived streams, you know, in the refinery. And then we just started to do some basic blending calculations and seeing how some of these upgraded intermediates can then blend into the finished product fuels. Okay, and then the bulk of what we're going to talk about today is really derived from this NREL-Petrobras relationship, where we got some excellent data from Petrobras's pilot units down in Brazil, and we built a pretty comprehensive techno-economic analysis around that data set. And then since that analysis, we have come a long way in terms of utilizing different tools. So with our partners at Pacific Northwest National Lab and Argonne National Laboratory, we've utilized some of Aspen's tools, specifically the PIMS refinery optimization model, to do a bit more comprehensive analysis and really trying to look at risk for the refineries. And we'll talk a lot about economic risk associated with co-processing opportunities here. Okay. All right, so now I'm going to dive into the NREL-Petrobras analysis. I mentioned that Petrobras performed some really great experiments with a very commercially relevant pilot unit. And as I mentioned, what we're really looking to do is leverage pretty substantial processing volumes, both in the US and of course globally. I realize that Europe is not necessarily FCC centric. I think historically Europe's been a lot more hydro processing heavy, but still some substantial FCC capacity there in Europe. So I think this is all very relevant. just a quick overview of what the FCC does. So the FCC takes generally gas oil range feedstocks and cracks them. There's a molecular weight reduction that's going on, but it also removes coke, right? It removes carbon. There's kind of two approaches in refinery unit operations for those heavy conversion units to increase hydrogen to carbon ratio. And that's kind of what we're doing in these major conversion units. And we're doing that in two ways. In the FCC, we're removing carbon. So we're making coke and utilizing that in the as reaction heat. Uh-oh, I'm getting a bad network quality. Am I still okay?
Yes, it's
Okay.
still fine.
Okay, thank you. Okay, so in the FCC and units like the cokers, we're removing carbon to improve that carbon, the hydrogen to carbon ratio. And of course, also doing molecular weight reduction to convert these heavy gas oil molecules into, gasoline and diesel range products, in addition to substantial volumes of light olefins and things like that. Okay, and then on the other side, hydroprocessing is all about adding hydrogen to improve that hydrogen to carbon ratio. So while we have a benefit of carbon efficiency in hydroprocessing units, we have that cost of hydrogen consumption as well. Okay, so in the FCC, we get obviously a whole slate of different things. So we have those light olefins, propane, propylene, the butanes and butylenes. Then we get into the naphtha range products, light cycle oil, which is basically the ultra low sulfur diesel precursor or any distillate range product precursor, and then some bottoms oil that is, I think, typically sent to like the heavy marine fuel type blend stocks. Okay, so a quick overview of the FCC. I do want to mention the conversion is generally the primary indicator of operational severity on the FCC, and it is simply 100% minus the yields of the bottoms oil and the LCO, and that's a metric that we're going to use throughout the rest of the discussion as well. Okay, so what did we do in this Petrobras work? So again, Petrobras has this really excellent unit to which they fed both traditional fossil gas oils with up to 20% pyrolysis oil. So the pyrolysis oils came from two different producers. Both Ensign and BTG oils were used in these experiments, and essentially the properties of the two oils were extremely similar. Now I realize there are very likely details between the two technologies that make a difference in terms of quality of the bio oils, but on paper they were very similar. So we actually combined all 54 of those data points into one giant data set and took these data sets and built statistically based equation based models for each one of the products. So what I'm showing here is just the FCC cracked naphtha experimental yields and the corresponding equation-based model that was derived for that cracked naphtha. All right, so where cracked naphtha is on this list of liquid products, and my point here is only to highlight that this is one of 12 different individual, what we're calling meta models that contribute to this overall FCC yield model. Okay, so we're at the point now where we're trying to get this data set in a way that we can utilize it for things like optimizations. And so I mentioned that we generated one of those equations for each one of those major components for the FCC. Of course, we validated them. So these are examples of, okay, how does the actual cracked naphtha yield prediction compared with the demonstrated experimental yields? Naphtha is the most substantial volume product that we get off of the FCC. So this is pretty much the highest scatter that we had for any of the products that we looked for in terms of trying to develop this yield model. So my point here is that we got pretty good correlation across things like the bottoms, the light cycle oil looks really good. propylene, which is also a very important one from an economic standpoint. We got very good consistency there. So my point here again is just to ensure everyone that we've validated these yield models before then trying to use them for subsequent analysis. All right, also in the scope of this techno-economic analysis was some product upgrading and finishing unit operations downstream of the FCC. So the FCC, we talked a little bit about how we get that full slate of different materials off of the FCC, and then subsequently in a refining environment, much of them, for example, the butenes and isobutanes are converted to a high-octane gasoline product through this process, alkylation. The FCC gasoline that comes from the FCC still has a good bit of sulfur in it, so it goes through some hydrotreating before we call it a finished gasoline blend stock. And same with the diesel products. There's some pretty substantial hydrotreating to get to the ultra low sulfur diesel product that we make in the US. And then depending on the quality of the heavies, that can, like I said, go to some marine fuel, or can go to subsequent hydroprocessing to perhaps make higher quality products from it. But this was the scope associated with the NREL Petrobras analysis. Okay, so now we're going to get into some fun stuff. When we put that yield model together, this is what it starts to look like. And this, when we see things like this happening, where we have curves going up and reaching an optimal point, like the cracked naphtha, and we see this light olefins yield trending up with conversion, and let's see, in the marine and diesel and all the products we have in sort of one mathematical based framework. And what we do is we take this mathematically based model and we kind of combine it with economics. So we've worked a long time on trying to understand how the economics associated with bio-oil processing, which are largely driven by the crude oil markets, impact the economics of our potential biofuels pathways. Okay, so once we have this comprehensive pricing framework that incorporates with our yield model, we can do good stuff. All right, and so I'm going to start with an illustrative example just to lay out how I'm going to discuss these results. But the first thing that we notice is our cost to produce bio-oil is really not a function of the crude markets, right? But the value of the products that we make from co-processing bio-oils very much are. So when a refiner accepts a feedstock and puts it in their refinery, the value of that material is a function of what they get out, right? So while our production cost for this biointermediate that we want to feed to the refinery is not a function of WTI or West Texas Intermediate or any benchmark crude, our value is. Okay, so when crude price is high, if we think about ourselves being in the driver's seat of the refinery, when crude prices are high, I have a really good potential to make some money off of putting this biointermediate in my refinery because the products are valued high. When crude prices are low, it's a very different scenario. And this whole phenomenon presents economic risk for the refining industry as we are trying to engage them in contributing to biofuels production. This is certainly a challenge that we have to understand. Okay, I hope that makes sense. Now I'm going to jump into some of the actual results. Oh, I forgot I had animation here, so sorry about that. Okay, so we've got essentially two scenarios that we're going to focus on. We've got this near-term bio-oil production scenario at around $80 a barrel of bio-oil, and that is the cost to produce that. This is a fast pyrolysis oil in this case at 400 metric tons per day. Pricing over here on a per meter cubed basis. I hope that's helpful for everyone, but I'm not very good in talking in these units, so I'm going to stick with barrels. dollars per barrel. So this is what we see as being sort of the current state of technology for pyrolysis units. We're in the 400 metric ton per day ballpark. We see that with Ensign and BTG as well. So what the economic results from the Petrobras work showed is at 5 weight % bio-oil in the FCC, there's a very real economic base or business case, if you will, that can make some profit for the refiners above this roughly $70 a barrel benchmark. Okay, so this is basically what we're considering a near-term economic opportunity. Right, then we've got down here a more mature biorefinery. So NREL, when we do analysis on what we call the nth plant biorefinery, the nth plant indicates that we're assuming this thing is mature. It's not the first generation biorefinery, but we've got somewhat mature technology. So this is kind of our representation of where we expect the cost of production would go long term. And so this puts us somewhere in the $50 per barrel bio-oil ballpark. Okay, and then we have our 10 weight % bio-oil curve. So it's important also to note that as we increase, at least based on this experimental data, as we increase bio-oil content in the FCC feed, we get slightly lower value yield products. And this makes sense. It's just part of the technology and part of the development, part of the learning curve associated with beginning to feed these materials to these processes. Okay, but even in this mature biorefinery scenario, we see, again, a profit opportunity at below, that's somewhere around $55 per barrel. Okay, these are the actual results. I'm going to jump back to the illustrative example here in a moment, but again, the same thing applies. Down here where this curve, the value curve, is less than the cost of production curve, these are the high risk areas for the refiners. Okay, I'm going to jump back to this the simplified curve and just give a very high level example of how we might use these analysis results to inform policy development. So our goal, at least from our standpoint, the goal here is to try to engage the refining industry to utilize the vast infrastructure capabilities to help produce biofuels. But this is the challenge. So we've got profit opportunity, but substantial risk over here. Okay, so now what if we theorized some sort of like how a policy incentive would look here on this curve? All right, and so the way that I envision a very simple application of policy to look is to increase the profit potential of this curve by some fixed value, right? So that curve just shifts up. So we have a higher potential for profit and a slightly lower potential for economic loss. All right, but this is still a big number, right? So there's a lot of space down here that could still result in a lot of risk, basically economic risk for these refiners. So how could we perhaps envision a policy that perhaps makes the economic loss a little bit more mitigated, but doesn't necessarily like elevate or I guess overshoot profits when the refiners don't really need help to realize these profits, right? So perhaps there's a way that we can design variable policy incentives that really take into account the fact that the industry needs more risk mitigation down here when the crude prices are low. And we're beginning to use our models to really try to assess the risk. So if we say that, again, very simple example, if we're going to say that this fixed policy benefit would look like this if we were trying to do essentially a Monte Carlo based risk analysis, doing something like a variable policy incentive that ties to WTI could really make the risk profile for a refinery exploring this as an economic opportunity much lower. So we're really trying to understand how something like this might impact the risk profile for these economic endeavors. Okay, so again, very simple example, and perhaps we'll have some questions on this. I just wanted to move into a little bit about how we've expanded our analysis capabilities a bit beyond just looking at the FCC, for example, within the refinery. So now we're using these Aspen PIMS models and really trying to do comprehensive scenario analysis by using, okay, well, what does our US refining infrastructure look like? What configurations and capacities do we have, and where are they located? What are the qualities of the bio oils and intermediates that are being offered by the emerging biomass conversion technologies? What are the fuel specifications that we're currently living within? You know, what do these fuel finished products need to look like? And that is all for us coming from ASTM. And that this also gives us the ability to look at perhaps emerging fuels, like in that Co-Optima project I mentioned. The consortium looked at trying to optimize fuel and engine mixes to improve efficiencies going forward. So we can look at new fuels, pricing and forecasts. So it's really important, I think, for us to understand not only what today's product demands are, but how is that going to evolve? Like, we know there's going to be a lot of electrification in light duty vehicles. So that, you know, we maybe want to reduce gasoline yields in the refineries, but diesel and jet, they're not going anywhere. Propylene and light olefins, there's demand for light olefins is going to go up. Marine fuels, and so we have to consider all of those things and not really focus on one product just because we know that we're going to have a whole slate of products to deliver on for our customers. Okay, I have to put in a plug for our experimentalists. So we have, in the last 5 years or so, purchased and installed this Davison circulating riser for evaluating co-processing. This DCR is actually really versatile unit, so we can actually do catalytic fast pyrolysis, so that with this same unit, and do co-processing. So it's a really neat unit. If anybody has any interest in trying to collaborate and utilize some of this equipment for co-processing experiments, NREL is always looking for new collaborations. So that's my little plug there for new opportunities. And really our future goal is to figure out how to utilize all this existing infrastructure out there. So we've got all these refineries scattered throughout the US and certainly the world, and all those, you know, refineries are connected through these pipeline networks too, which are very, very valuable for us if we can figure out how to utilize them effectively. Yeah, we have a lot of collaborations with industry. That's really, I'm very thankful that those relationships are beginning to come to fruition, because they are really proving valuable, and I hope will help with commercialization in the near term. And we think this kind of analysis can really help with informing effective policy design. So we'd really love to, you know, start having meaningful discussions around utilizing this type of analysis to assist in policy design. Okay, so right now, obviously, we focused a lot on the FCC, but we've got all of these emerging technologies that can produce different bio-oils of different qualities that have really different benefits in the refinery when you feed them. And looking beyond just the fuels is important. We have olefins and aromatics and other chemicals that we're going to need to produce. So let's leverage the refineries to do that as well. It's obviously, I've focused on economic analysis here, but the co-optimization integration of environmental and economic calculations is absolutely imperative. So that's the direction we're headed to really make cost of carbon sort of part of the economic optimizations, right? we're focused on hydroprocessing. We'd love to move into other insertion points. The resid FCCs are interesting, delayed cokers, fluid and flexi cokers, and certainly there's this very low sulfur marine fuel evolution that is taking place. So how can we utilize these models and this type of analysis to help with marine goals as well? And then lastly, we're really focused on trying to figure out what the best allocation of all of our bioresources and circular feedstocks might be. So that it's a very complex math problem. We've got lots of emerging technologies that can really help, and we've got a full slate of products that we need to deliver. So understanding how to produce those products from a very diverse slate of feedstocks and an interesting mix of emerging conversion technologies is a very cool optimization challenge. And so that's where we're going to spend lots of time going forward. Okay, some publications and acknowledgements, and lastly, questions. And it sounds like we may save those till the end. So I'll give it back to Patrick now.
Okay, thank you, Michael. Thank you for making such an incredibly complex subject quite in a quite short time. Give a very good overview of it. Thank you for that. There are many questions also for me, but if it's all right with everybody, I propose that we first do the presentations and then combine the questions all at the end. Is that okay with everybody?
Sounds good.
Yeah. Okay. So thank you, Michael. We go to the next subject. That is one of the first case studies of the Biofit product, the integration of HVO production in the Thessaloniki refinery of Hellenic Petroleum. Dimitris, I see that I give you the word as first.
Yeah, hello. Thank you, Patrick. Thank you very much. This is Dimitris Kourkoubas from CERT. I'm working as a research engineer, and as Patrick mentioned, LP was one of the case studies in the Biofit project, and CERT leads this one. I will share my screen, and then I will give the floor to my colleague Eva. Please let me share my screen. And just, sorry. Yeah, I think that you can see my screen and turn off my camera, and also in full mode. Okay, hope you can see my screen.
Yes, perfect.
Perfect. So this presentation has two parts. The first part, my colleague Eva from LP will describe and will provide to you the LP strategic plan, relevant activities of LP, while on the second part I will describe in brief the Biofit use case. So Eva, please introduce yourself and let me know about the presentations in order to scroll down the slides.
Okay. Hello, everyone. I'm Eva Nanaki. I'm working as a researcher in the Hellenic Petroleum. I work for the industry during the past 15 years, and I'm involved in many research programs in regards to alternative energy fuels and new technologies. So I'm going to briefly present you our strategic plan in regards to the vision of 2025. And as we see, the global energy landscape during the past year is going through major shifts, and the energy systems are going through some rapid transition. transitions. In regard to the legislative and regulatory framework uncertainty, we have some technological maturity of candidate solutions. There are significant investment risk and funding, and also we have the sustainable raw materials availability issues, and then we have the time pressure to find the adequate and sustainable energy solutions for our industries. So, Hellenic, the refining of the future, Hellenic Petroleum is strategic goal is to become a provider of low carbon energy solutions and to reduce its carbon footprint by 50% until 2030 in order to contribute in addressing the issue of climate change. In this light, the group launches the Refinery of the Future, in which innovation technologies are going to be developed with the use of new raw materials, renewable energy sources, hydrogen, and of course recycled CO2 are going to be used. Our aim is to produce low products of low impact, low greenhouse gases products, and low carbon fuels. So in this area, in this slide, we are involved in many. Dimitri, if you can proceed to the next slide, please. Okay, in this scope, we have developed a strategic research and innovation scheme during the past years. We have started to participate in many research projects in regards to energy issues. These projects are not only focused within the Greek territory, but also we're involved in many European projects, including Horizon, Life, and etc. We have involved into a team that defines and proposes research projects according to the strategic vision of HELPEM. Our areas of interest are, in the first place, the reduction of CO2 emissions, the digitalizations in the refining sector, the development of low carbon fuels, the energy storage, of course, everything that is involved with renewable energy sources, and of course, the e-mobility issues. We can indicatively refer to some projects that we have been involved in the past years, and we can categorize them in the areas of biofuels. These include the projects of HYCON, of Circ4Bio, alga fuels, B2BioRef, alga biofuels. The main concept of these projects are mainly the development and of second generation biofuels. In these projects, we're mainly the end users. So we're involved in projects that refer to the refineries of the future for the creation of low carbon fuels, such as the Desulfur, the Prometheus project, Zeocat. Also in projects that refer to the energy efficiency and the digitalization. The production of green hydrogen and most recently of blue hydrogen also, the development and coordination of biorefineries such as the BioFit, and of course projects that involve the training and education such as we're involved in Erasmus project and the PhD Hub project. So also, not least, we are involved in the big project of White Dragon. This is a huge project of 8 billion euros. This is a project that involves the production of hydrogen. This is an environmentally friendly hydrogen as fuel within the IPCI's in the context of the Hydrogen Europe program. And this is a project which involves big companies such as Vespa, Motor Oil, Mytilineos, Terna, the Polish company Solaris, and also major research institutes such as Demokritos and, of course, CERT. So, Now, my colleague Dimitris is going to present you everything that concerns the BioFit case study in detail. So, Dimitris, if you can please proceed.
Thank you, Eva.
Thank you very much.
Let's continue with the BioFit project. Okay, here it's the description of the LP case study. The main scope is the integration of HVO production in the Thessaloniki refinery. So the unit is currently used to desulfurize the LGO stream coming from the CDU, stripper column, and the UCO will consist of 5% volume of the processing mixture. So, as a result, an annual production of 22,000 tons HVO is expected. HVO can be characterized as a premium drop-in fuel that can replace diesel without modifications to existing refueling systems and/or vehicles. Here it's in brief, in a schematic, the technical description of the suggested retrofit. As you can see on the left, here it's what we suggested with the partners involved in this one, in this project. Technip Energy in specific, we suggested as a retrofit for introducing UCO. UCO using cooking oil. Here you can see all the intermediate stages for the treatment in order then to blend with light gas oil to the light gas oil hydrotreating system. Regarding now the technical description, the methodological approach that we follow about the technical description, in specific mass and energy balance carried out for the current situation, the light gas oil hydrotreatment system unit, while in identification of the requirements of the suggested retrofit of for co-feeding used cooking oil to a hydrotreatment unit have been defined. There was a discussion and identification of the existing equipment and, of course, which are the new items that should be installed at the facilities of LP. Then about the supply chain assessment and market analysis, here BEST was the main partner. The methodological approach that was applied was first of all to identify and this UCO quality and UCO prices. We give emphasis, of course, in Greece and on a related legal framework. And these are the main issues that we discuss within this report. First of all, about the collection and supply potential of UCO in both the professional sector and domestic sector. About the production capacities in European countries, including Greece, for especially for HVO, of course, for HVO and UCO-ME, about the UCO trade and UCO imports to other European countries, including Greece, and in addition, the current rules and legislative framework. About the economic assessment, here BTG was the main partner, and a cash flow analysis was carried out in order to calculate the main economic indicators, namely net present value, the internal rate of return, and payback period, in order to find if this investment is sustainable in financial terms. Finally, environmental assessment that CERF was the main partner. Here we calculated the saving emissions compared, first of all, to the existing scenario, to the current scenario, to the current operation, while also we calculate the savings of a full conversion, let's say HVO, and only, let's say, HVO production plant, in order to compare this one with the RED II directive and the fossil comparator, that it's about 94 grams CO2 equal per megajoule. We used for this reason the equation that is provided in RED, and of course all the equations about the savings. So here we can see the major findings, the main findings of a BioFit project. First of all, about the supply chain assessment. As you can see, the current UCO collection in Greece is not sufficient for co-processing. Even this one is a high fresh oil consumption. Even it's a country, Greece, a country with a high fresh oil consumption. So the UCO import from other countries is required. The import from third parties is not limited, but a certification of origin is required. Long-term contracts are a good options to secure supply and the price, and the suggested retrofit is within the 1.7% cap of RED II. Regarding the economic assessment, based on the equipment that was selected and some assumptions that made, the investment seems financially attractive, with a higher IRR and payback period quite, let's say, that it's low, and means that this one, the investment is financially sustainable. Some main considerations that are made was about the buying price of UCO and the selling price of the green LAGO product. Based on this, as you can see here, we have some indicative prices for the maximum UCO buying price, about 800 per ton, and minimum green LAGO selling price, about 1,200 euro per ton. We concluded to some good results for the economic assessment. Finally, about the environmental assessment, the co-feeding was, as we said in the beginning, 5% per volume for the facilities at LP. And the greenhouse gas emissions was about, the savings was about 4.2% compared to the current status. The construction, as we said in the approach, the construction of a new refining unit using 100% UCO as a feedstock presents significant emissions, about 86% compared to the RED II comparator. Further investigation with respect to environmental impacts of a green fuel production process can be carried out, while due to the max cap of UCO usage imposed by RED II legislation, alternative sources of biofeedstock will have to be considered. Yeah, and here it's our last slide about the barriers and opportunities. So on the left, we can see the barriers. We can say that, first of all, a main barrier for this type of investment, we referring to the Greece case study. Okay, so it's the location for UCO collection point, and Then not, let's say, we don't have a central collection points from a household, so this one is quite a barrier for this investment, this type of investment. Lack of knowledge on environmental effects of dumping versus collection of a UCO. There is an uncertainty about the income for collectors due to the fluctuating UCO selling prices and supply volumes in the professional sector. In addition, the traceability system for the collectable UCO, especially regarding the amounts produced from household, is not very well known. Lack of infrastructure and fuel quality standards, not a well-defined political framework regarding the UCO import and quality standards. The low collection efficiency of UCO originating from the household due to the lack of logistics. And yeah, as we said also previously, lack of regulations in the legislative framework in Greece. Regarding now opportunities, of course, this one is a great opportunity for the energy transition in order to reach the targets set by European Commission. It's an economic value of UCO as a resource, competitive price of HVO compared to other alternative fuels, higher HVO fuel efficiency and chemical structure identical with petroleum diesel, and finally cost-effective production of HVO, but it does not require, as we investigated, as we describe also in the technical part, an expensive technology investment as other biofuels do. That's all from our side. Thank you, and of course we are at your disposal for any questions that you may have. Thank you very much.
Thank you. Dimitros, it's very nice to see the results of the case study, and what we see indeed economically it's quite feasible, but as you see more with quite regularity that the feedstock availability and the way in which you can treat it and certify it is a very important point of the entire value chain, and it can indeed sometimes be a limiting factor. I'm sure during the questions we will get back to that. For now, I propose that we continue first with the third presentation on the second refineries case study. That is about the case study on the Total Energies refinery. Gail, are you there? Okay, I don't hear or see Gail. Good. Maybe she will come back later. For now, then, I think what we can do is we can, if Michael and Dimitros and Evankia are there, please join me and we can, I think, discuss the questions, comments regarding the presentations that were there. Yeah. Michael, if I may start with you. Sure. I saw one question regarding a question from Luc Pelkmans about the bioorganic content in the products from which you get from the co-feeding of pyrolysis oil. How do you count the green molecules in the final products?
Yep. So absolutely a great question and super relevant for any discussion that involves co-processing. And this is a hot topic in the U.S. as this really, I mean, to me, this is a a deal breaker in terms of whether a refiner would have sort of a positive business case or not. And so the methods that we looked at in our analysis were the carbon 14 based analysis, which for fast pyrolysis was substantially lower than applying just a simple mass balance to quantify the apparent yield structures, if you will, from fast pyrolysis oil. So in a mass balance, we would just assume that the base feedstock yields from the VGO or whatever gas oil feedstock is going into the FCC would remain constant, and then apparent yields would just be calculated by the 5%, 10% increments by which you're feeding the bio oil. And that approach is very straightforward. Refineries are already equipped with the instrumentation to do that. And my understanding is that it depends on which policy we're talking about. So the RIN, the EPA incentives, I believe, are still based on carbon 14. They really want carbon 14, whereas the LCFS in California, as I understand, is maybe moving towards the mass balance. And I think the industry is trying to work also with our EPA in justifying the relevance of the mass balance approach. But that's essentially where we stand. Is the carbon 14 sets one bookend, and then the mass balance approach is certainly preferred by industry and deemed lower cost and reliable. Was that sufficient response? Did that answer the question?
Yeah, well, I think you can write a book about it.
Mm-hmm.
Maybe just one short comment on this is that BTG Bioliquids, Thijs Lammens, wrote a white paper on the use of, or a paper on the use of carbon 14 for determining the bioorganic content in the liquid fuels. And his conclusion was that at these low co-feeding quantities, that the carbon 14 method is difficult. Mm-hmm. It's not so much that the method itself is unreliable, but it is because of these small quantities, the level of unreliability becomes still high. I'm not sure. Do you know about that?
Yeah, definitely. I'd say that is directly in line with our observations. And we, I can provide some additional resources for how we've quantified them. We had some meetings with both EPA and the California Air Resources Board where we discussed this exact topic, and those are out in the public domain. So I'll try to find some one or two of those and just post them in the chat if that would help.
Yeah, certainly that would help. Yes. Are there any other questions or comments regarding these first two presentations, or maybe more general?
Patrick, if you allow, Rainer Jansen from Munich. I would also have a brief question to Michael. Many thanks for this very interesting and detailed presentation. You were talking about these variable policy benefits that could be placed to help the industry with risk mitigation. Could you give an example, sorry, of how that could look like? Yeah, I assume that you have looked into more detail, right? Just to give some flesh to the bones, how could that be done in your view?
So I'm purely an analyst, and so or engineer, I guess, engineering analyst type. But how implementation of such a thing would work is an excellent question. But it is quite straightforward from a conceptual standpoint. It just would suggest that there there is consideration in a RIN or a policy credit that is there's just essentially weighting where it would be higher weighted when crude benchmark prices are low, and therefore creating just a challenging environment for refiners accepting these feedstocks that, again, don't really tie to crude markets. So I think in application, the concept is very simple. It just is not a flat value that is constant all the time. I think that's
so basically
that's
just include the crude oil, the current crude oil price in the calculation formula for credits.
I think it does, yes.
Okay. Thank you.
Yeah, of course.
If I can pick
Luke,
in, maybe.
Please go ahead. I saw you raised your hand electronically, which is indeed very helpful.
Yeah, just to pick in here also, I think this sounds a little bit like contract for difference mechanisms that you have, for instance, in the UK, where the support for electricity in that case depends on the electricity price. So I think that's pretty efficient. Also, we also see it now with the increasing electricity prices that they actually need less support in this case, and in that case the support is also reduced. And yeah, here in Belgium we have a fixed support rate, and there's a lot of criticism now that they get they're actually paid to get a lot of profit from public subsidies. So getting a variable component there is really a good idea.
I'm glad to hear there's a similar data point. That's great. Thanks, Luke.
Yeah, maybe I can also put in another data point there. We have in the Netherlands also a variable support, the SDE++, nowadays it's called. And that works in the sense that if the market prices are higher, support indeed goes lower. And now we see an interesting phenomenon because there are a lot of projects have been awarded for CO2 carbon capture and storage, and they tend to will likely require a lot of less support. And that means that for the entire period, the support is less. And the point there is that people say, well, yeah, that means that of the budgets that we have allocated, we have a lot less to give to this. And yeah, is that effective? I mean, it's a luxury problem in that sense, but it is, of course, if you make it dependent on these market developments, things can change, and your allocated budgets, it's not entirely clear if they are all used. So that's also a point which you can have.
And just in the preliminary analysis that we're touching upon so far at NREL, when you apply the variable policy concept, the result total mitigation cost, we kind of call it mitigation cost, which is essentially the part that the technology is going to develop and sort of accomplish in cost reduction, and then there's the help needed from policy as well, and they're kind of one and the same. Or would, I guess, starting from year 0, we have much more policy, and then in year 50 plus, then we expect that policy to phase out and technology development would take its place, right? But what we're seeing is that it doesn't take overall more based on historical market volatility. Like the total purse requirement is almost the same if we can apply a variable policy. So cost to the consumer or cost to the taxpayer, we don't think that's substantially higher with these variable policies. It's just the way that it mitigates the risk.
Reiner, please go ahead.
Yeah, thanks. I have another question to Michael. Maybe this one is a little unfair, but I'm interested to hear your views on that. So basically, what you were talking about was a mixing of up to 20% of pyrolysis oil in order to benefit basically from this large FCC capacity just for the production of biofuels, for instance, for aviation, which we need, as we know. What would your argument be if saying, okay, if we are looking at total decarbonization rather soon, in fact, what will happen with the 80%? You know, will we move forward? Will this, you know, will that be 20, 30, 40, and then 100 at some point, or do at some point we need really totally different approach, which is then postponed to the future if we co-feed?
Yep. So I think all of those are yeses. I think there's it, you know, if we begin down the path of co-processing, I think that leads to repurposing. Oh, we're already seeing repurposing, right? We're seeing repurposing for the low-hanging fruit, which in the US is the fats, oils, and greases. And essentially those resources, as I understand, are pretty much gone, or on paper, they're gone in new projects, right? I think the co-processing starts down the path of further repurposing, I do, and complete transition to renewable feedstocks over time. That is certainly the concept that we're working with. But again, how that happens, I think, is just a much more complex thing than we really realize. And so my hope is that capabilities and interest in looking at this as a holistic, hey, we have to make all of these products ultimately from these renewable feedstocks, you know, that's a good place to start. And then I do think that you know, technologies that are going to change the game are absolutely needed. I mean, I don't see a path to decarbonization, especially not in a hydroprocessing centric approach that doesn't include very reliable green hydrogen. I think there are a lot of you know, related challenges that have to be approached, yeah, like holistically.
Thank you.
I'm sorry to give such a vague response, but it really is a really complex thing.
No, exactly. Yeah. No. Thank you. Much appreciated. Yeah. Thanks.
Of course.
Good. Then, Michael, yeah, you're here, so you are really. It's very nice to ask you all these kinds of questions. Just a practical question. You, in your economic calculations, what price did you take for the pyrolysis oil?
Okay. Yep. So that really kind of is also a variable. So these lines represent our techno-economic analysis estimates for the pyrolysis oil intermediate. So at 400 metric tons per day, what we're estimating is around $80 a barrel, or $500 per cubic meter. And then in the long term, the estimate here for this analysis is $50 a barrel. And this is raw pyrolysis oil for this analysis. So we're talking up to 50% oxygen with the water that's still present in these materials. So there's water and a whole bunch of oxygen. And then for NREL's research program, the pyrolysis process is really almost a spectrum. So, you know, we focus also on catalytic, coupled catalytic processes that improve quality, but of course have that impact on lower carbon yield. But we're trying to find that optimum point for the quality of the bio oil transitioning from the biorefinery to the refinery.
Can you repeat that last sentence?
Yep. So this is, of course, this whole analysis with Petrobras is based on fast pyrolysis oil. Mm-hmm. But NREL is really heavily involved in research to look at coupled upgrading of, the raw pyrolysis oil to lower oxygen content intermediates. So we do believe there's kind of an optimal in there somewhere between deoxygenation at the biorefinery and sort of reliability of operations in the petroleum refinery, if that makes sense.
Yeah, to paraphrase, you are also looking at partial deoxygenation of the pyrolysis oil.
Yes.
And that is facilitates co-feeding, of course. And there is an optimum somewhere. If you fully deoxygenate, you hardly need your FCC.
Exactly.
And if you don't do it at all, then your FCC gets a lot of coke to swallow.
Yep.
Yeah. Okay. And on this graph on the right, you showed indeed the expected price of the pyrolysis oil in dollars per cubic meter bio oil. Yeah.
Yes.
Okay. Clear. Yeah. No, I think those are reasonable ranges, if I say. There is a question from Thijs Lammens. Thank you for your hand. Please go ahead.
Thanks, Patrick. And also thank Mike for a very interesting presentation. I think it's really a tremendous amount of data that underlies it. So it's a pleasure to hear. And I have one question, because you base your model on this data set with Petrobras, and I think it's a very extensive data set. But still, it makes me wonder, what is the impact of the fossil feedstock that is used in this case on the product slate, on the yield plate? And if you would do this same analysis for a typical European refinery or a US or a Chinese refinery for that matter, would that change? Because of the changed yield plate, would that change the break-even value significantly, or do you believe that doesn't really have a significant impact?
Great question. And I believe that based on what I'm seeing in new data sets, I think the quality of the bio oil dictates its true value, but the co-processing, first of all, the unit operation and the corresponding base fossil feedstock is also pretty important, at least, and especially in these early stages of co-processing, because the insertion points, I think, have a lot to do with the ultimate risk, and the risk being the reliability of the operations, right? So if a pyrolysis oil or any bio oil is fed to a refinery or any unit, and there's immediately negative consequences that impact that refinery operating, that's really bad for the refinery, and it's really going to look bad for that bio oil too. So I do think that both are really important. My suspicion, educated or informed suspicion, is that the bio oil quality will really be the driving factor in its value. But I'm super interested. I think there's tons of optimization opportunities. We've looked only at the FCC without a cat feed hydrotreater. I'm really interested to see how hydrogen changes the game in an FCC, particularly with co-processing. I don't think I would necessarily feed pyrolysis oil to that cat feed hydrotreater, but I think there's a lot of potential benefits in the yield structures associated with feeding pyrolysis oil to the FCC that has a cat feed hydrotreater on the front end of that FCC, providing hydrogen to the bulk fossil feedstock.
Yeah. Okay. Interesting. Thanks very much. Yeah.
Yeah. Maybe just as a follow-up question, you mentioned the bio-oil quality is crucial. What are you referring to? Like characteristics like homogeneity or particles, solids in it, or do you mean composition like CHO, etc.?
The most of the data that we have is really a function of elemental composition. So how much oxygen has to be rejected and how much hydrogen is there to begin with. That said, I think there are the deep devils in the details, Patrick, as I think you are getting to, metals and particulates. All of those things are hugely critical in the reliability aspects. And cost, of course, like metals are going to dictate the catalyst consumption rate as well.
Yeah, certainly, indeed, yes. But my question was indeed more the general question, like is it anything else than those parts? Yeah. No. Thank you. I just also one question for a European audience. You are doing this work very diligently, and it's indeed what Thijs said. It's clear that a lot of work is going into it. So there must be also good reasons for doing that. And we do not know, at least I don't know, what the status is for this co-feeding in the US. Are you aware of pilot projects or full-scale projects that are being implemented?
So I'm not. I don't think I'm allowed to speak specifically about projects, of course. But yes, there is activity, and there is industry interest in at least developing these as business cases. I don't believe there is. I don't know of anybody actually, feeding these materials to an FCC on a daily basis at this point. And then, of course, in the US, we've had a real shift to sustainable aviation fuel focus. And so I think that naturally puts a lot of emphasis on hydroprocessing. But I guess I tend to go back to in 50 years, are we only going to be producing sustainable aviation fuel from our fossil and or bio-based facilities? I'm guessing not. I think we're going to be making some other things as well.
Okay, but indeed, yeah, just as for the current activities, there is activities, but not really like it is splashed all over the newspapers. Yeah, of course, we would have seen it. But, okay.
And I do think that policy is a really important aspect of it, and there's lots going on in that space. As I understand, I'm not directly involved. As I mentioned, I'm focused on the analysis and hoping to inform, provide insights from the analysis, but not deeply involved at all in policy development.
Yeah, no, that's clear. That's clear. Yes. Okay. Are there any more final questions?
Patrick, thank you very much for having me.
Yeah, okay. Thank you very much.